Okay, can the people online hear me?
We can.
Okay, excellent, thank you. Okay, let's get started. I need to do something more. What did I need to do? Ah, certainly share my screen, that's for sure. Yeah, okay, so basically there was a question about the GPU training tomorrow. So that's a different training, so that's also a different link. I still have to send out the information to the participants. So if you want to participate in that training, no problem. Send me an email. I'll add you to the list of participants and you can still join. I'll send the email with the information somewhere this afternoon, as early as possible. So basically, that's one thing. The other thing is I posted the link to the website/repository for this training again, just for those who either didn't see it yesterday or just as a reminder, so just for your convenience. Okay, let me share my screen. Okay, and let's continue where we left off. A couple of remarks about things we discussed yesterday. So basically, for those interested in PyBind 11, there are a couple of more examples in the source code directory in the repository that highlight a few details that I didn't mention in the slides. So basically, feel free to have a look at that. It's, yeah, I would say pretty self-explanatory, but still, the interesting thing which I actually should add to the slides is interacting with NumPy arrays from your C code. So basically that is something that I should put in the slides as well. I did a few other checks. I did a check on Numba. So apparently something interesting is going on, but use it with caution. So basically, they also now have a decorator for classes, which basically means that you would get a compiled class out of your decorated Python class. However, that is experimental. So yeah, I would not recommend to use this in production. I'll keep an eye on it, and well, as soon as it's no longer experimental but production ready, of course, I'll add that to the slides. That would be nice if they were to support that, because that would be another thing that Numba can do automatically, for which at the moment you would require Cython. With respect to Cython, I also did a check on that. Remember, on the one hand, the Python approach, on the other hand, the PixFile approach. So apparently the Cython developers changed their minds. The stage last year was that they intended to replace the whole Pix thing. Now the message is no, oh no, we're not replacing the Pix thing. The Pix thing remains the main focus, and the Python stuff is just there for convenience, and yeah, maybe you shouldn't rely on it that much, etc., which is bloody annoying, because I adapted the slides specifically because they used to mention something different in the past. But anyway, so that means that I will update the slides again, taking out the pure Python, well, reorganizing things, basically having the whole story with Pix files, and then adding a section, a subsection on the Python thing. So mostly to make people aware that it's possible, rather than that apparently it should be the way forward into a bright future, which apparently changed 180 degrees direction. But okay, probably they ran into a number of things which they didn't manage to do properly in pure Python, and hence decided to adapt the documentation to reflect their, let's say, how do you say this in English? Okay, anyway, can't remember the idiom for it, but nevertheless. Okay, so we have touched upon parallel programming a little bit in a very easy way in Cython, using the p-range function, which is defined in Cython, which gave you a level of parallelization which is fairly trivial. It's just parallelizing for loops, and it translates to OpenMP, and essentially that's it. So that's one way to parallelize things. Another way to parallelize things, of course, is just doing that in the obvious ways in C++ or in Fortran, and then basically wrapping that code into a Python module, either using Swig, using F2 Py3, or PyBind 11, whatever mechanism you choose to use. So that is definitely another avenue to get parallelism. There is at the moment a project going on to bring OpenMP-like parallelism to Python. It's very much work in progress. It's something that at this point in time I'd not recommend for production. So it's something to keep an eye on, because if they get it to work properly, it will be very nice. But at the moment, well, okay. Let's not go there. So what else can we do if we want to leverage multiple cores in Python? So of course, using libraries that do that under the hood is your easiest way forward. And essentially, libraries like NumPy can do that by leveraging, for instance, a BLAS library, which is parallelized for using multiple threads, doing matrix computations. Of course, if you use polars, for instance, rather than pandas, you also get multi-threading for free. So yeah, that's the easy way. So more in general, if you want to roll your own, then of course, let me first make the chat visible. Otherwise, I'm blind. So, okay. If you need or want to parallelize yourself, there are a number of options in Python without going experimental. So basically, what do you want to do? I mentioned this. Basically, what do we want to do? Essentially, you want multiple threads of execution. Basically, each of these threads can do something different, like happens on your typical machine when you run a desktop, and there is a browser opened, for instance, Chrome. It will have multiple threads. One thread is going to be responsible, for instance, for updating the current tab in the current window. Other threads will be responsible for getting updates from the web, to listen to your input, that kind of thing. Listen, I mean, listening for events, not to your voice, of course. And basically, all these threads have their responsibilities, and they collaborate in some rather sophisticated way. And that is something that you can program natively in many programming languages, including Python. So Python, in its standard library, has a threading module, which you can use for that purpose. Remember though, in Python, if a thread accesses an object, no other thread can. Other threads have to wait until the object is released or no longer in use by the thread which is currently handling it. And that, as again, is the consequence of the GIL, the Global Interpreter Lock. So yeah, that is limiting in a way what you can do with parallelism in Python at this point in time. So the threading module is an option, but I'd say unless you have a very good reason, don't go that way, because it is rather low level. And it's something that, for instance, in C++, where you can also just use a threading library, it's even part of the STL nowadays, I would also not recommend to do that in scientific programming, because typically you want parallelism at a somewhat higher level, at a functional level that is more useful in scientific programming. Okay, so what can you use in Python? Well, again, in the standard library of Python, there are two modules, multiprocessing and concurrent futures. And both of them offer you options to do parallelism. So personally, I'd recommend those rather than using the threading module directly. Okay, so as I already said, you are limited, or Python is limited by the global interpreter lock. So that is a little bit annoying. So of course, it does not influence libraries that are threaded under the hood. So if NumPy uses OpenBLAS under the hood or Intel MKL, those libraries are threaded. That has nothing to do with the global interpreter lock, so that keeps on working quite well. That's not a problem. Now, given the global interpreter lock, it's best in Python for scientific computing to actually, rather than use threads, use multiple processes. Okay? Sounds weird. What's the difference? Well, basically, a process, if you look at it in Linux terms, and it's similar on the Windows and other operating systems, a process has its own memory space. So basically, the process kind of lives in isolation, and the process can consist of multiple threads. It may have a single thread, it may have multiple threads, but processes can share data, but normally don't share data. To make them share data, you have to do some work. So the advantage of that, of course, is that if you run multiple Python processes rather than threads, that liberates you from the global interpreter lock up to a reasonable degree. So that actually is quite useful. And then, of course, that helps you overcoming that limitation. But of course, that means that you are essentially running multiple Python interpreters next to one another. That data sharing is not so trivial, and that eats memory. It also adds overhead because creating a process is much more expensive than creating a thread. So basically, there is a trade-off involved. So that means that if you use processes, fine-grained parallelism, where you have very short computations that run in parallel, and you would do that regularly, so you would do that in a for loop, that would accrue quite a bit of overhead. So basically, your parallel computation should take sufficient time, should have a sufficient load, let's say, in order to offset the overhead created by spawning multiple processes. So that's something to keep in mind, that that is a limitation which is imposed. So let's have a look at NumPy first, in the sense that how well do things work. So I already mentioned the underlying libraries. So basically, if your code is quite heavy on, for instance, matrix-matrix multiplications, or other linear algebra problems like solving linear equations, or matrix decompositions, be it singular value or QR or whatever, is supported by SciPy, then basically things kind of happen automatically for you. So, for instance, that is a free lunch, and if you do that, in this particular case, the experiment is based on Intel MKL, but that also works for OpenBLAS. It just so happens that I had this installed. So basically, if you look at this graph here, this is a matrix multiplication. So on 1,000 by 8,000 by 8,000 matrix. So it's a pretty large matrix. As you can see, this is the number of cores, and this is the speed up. And as you can see, this is not too bad. For 16 cores, you have a speed up of 12. It's not brilliant, but it's okay-ish. And of course, this is for free, in the sense that I didn't have to change any line in my Python code. It just works by, under the hood, using an appropriate library. And as you can see, if you cast that into efficiency, parallel efficiency, then you see that, for instance, with 4 threads, you're still at 90%. So that is quite reasonable. Okay. Of course, you can try different things. If you try SVD, so singular value decomposition, you see that it doesn't scale that well. So basically, you see that indeed you get a speed up, but it rather rapidly starts to flatten out, and then it even decreases a little bit. Okay, that is because SVD is not so easy to parallelize and doesn't scale that well. So this is not so much due to an implementation, it's just due to the algorithm, which doesn't lend itself very well to parallelization. So if you cast that in terms of parallel efficiency, you see immediately that that drops rather dramatically. For 16 cores, you're actually below 20%. And that is really, really low. So basically, I would say this actually hardly scales, because even at 2 CPUs, you're at 70%. So that's not so very brilliant. Okay, so that would be SciPy on top of NumPy, and hence on top of LAPACK and some BLAS implementation. Of course, in this case, again, MKL. And in this case, since MKL also contains LAPACK, in Intel's implementation of that, basically that means that you are using a proper library, but unfortunately the algorithm is not really the best one to scale. Okay, so free lunch, easy. The only thing you need to do is to make sure that your Python installation is or contains or is built upon, depending on how you view that, a proper underlying library. Remember one of the first slides. So basically, if you use the Intel channel, that is of course going to happen automatically because that will install the MKL runtime. It will make sure that NumPy actually uses that to do its computations. That's not the only way. You can also simply use an arbitrary SourceForge CondaForge channel. It doesn't matter as such, but then make sure that indeed you have OpenBLAS or Intel MKL as a backend. That's the important part. Okay, so not free lunch is multiprocessing, so then you need to do a bit of work yourself. So not to always do examples in, let's say, strictly mechanical computations. Let's do something different in this case. So I've got a very large file that contains DNA, and it's encoded as a large text file with just the ACGT, the usual thing. And what you want to count is how many of these nucleotides occur in that file. So fairly trivial task. And of course, if you can split your file somehow, then of course it's trivial to parallelize. So basically, the first worker looks at the first half of the file, the second worker looks at the second half of the file. They each count, and afterwards you just add the counts and you're done. So this is really trivial to parallelize. So let's see how to do that using multiprocessing. Okay, so basically it's quite simple. Each of the process runs over its data, and then you aggregate the data, and you are done. Okay, so basically we need a function that, given a chunk of data, is going to produce the count. Okay, so we define such a function, count chunk, and at the end of the day, it will return a dictionary with as keys, of course, hopefully ACGT, and as values the counts that this particular chunk contained. Okay, so the arguments are file name, start position, and chunk size. So all the workers, let's say, operate on the same file. That's not a problem because the file is only open for read. Many processes can have a file open for read. That's not generating a conflict, so that's not an issue. So basically, that's all fine. So we need to do a little bit of bookkeeping. We need to make sure that each worker gets a unique start position, and that, of course, the whole file is covered. That's basically the idea. But here we are only concerned with the function that, given the start position and the chunk size, which is just the number of characters to process, and the file name, does the right thing. Okay, so for technical reasons, it's easier that we just use a tuple as input and then unpack that. So basically, args is going to be a tree tuple, where the first element is the file name, the second is the file position, and the third is the chunk size. I'm just using automatic tuple unpacking in Python. So yeah, this is going to fail if args contain contains different number of values, but okay. Then we define a counter. Yeah, that's just a dictionary, and we simply initialize everything to 0. Then we open the file, okay, and we position the file. So basically, you can position the file just using the seek method on it, and the position, which is computed somewhere, which in this particular piece of code we don't care about what it is. It's just going to point to the right location. And then we read the chunk size. So basically this is a binary read, and it's going to read this number of characters, and it's going to store them in DNA. And then basically it's just iterating over that string, which we've got now, and if it's a legal character, then we increment the counter, we return counter, we're done. So no surprises, this is very trivial code. Okay, this was making sure that some work can be done. So how do we divide the work? So basically, that happens here. So this is a function count nucleotides. As you can see, it takes 2 arguments. The file name, yeah, no surprise. That's what is going to be counted, so that's pretty trivial. And then the pool size, okay? So what's the pool size? Basically, that is the number of processes we want in order to do the work. So if pool size is 4, then we will have 4 workers which can process this file. Okay, that's good. We get the file size. Probably there is a more modern alternative for this, but okay, let's not go there. Then we get the chunk size. Notice I'm here for convenience just assuming that the chunk size divides the file size. That's a simplifying assumption. It's easy to make sure that the file is totally covered if that's not the case, but that would complicate the code on this slide considerably, so I'm not going there. I just do it into the integer division, and I hope for the best. Okay, so basically, then we compute the offsets, and that's just a range at the end of the day, starting from 0, going by chunk size, with as maximum, of course, file size. Okay, then we get the arguments, and that is the arguments. It's a list of tuples, and that is going to be the arguments for my workers. So basically, each tuple will, of course, contain the same file name. It will contain the same chunk size, but each will contain a different offset. And those are the offsets which we just computed here. Okay, so essentially I will get a list of tuples with file size 0 chunk size, file size chunk size plus 1 chunk size, etc., up to the end of my file. And I will get as many as there are threads in the pool, or sorry, workers in the pool. Let me be general, because this is the computation of the chunk size. So basically, the pool size is determining that. All right, then the actual work starts. All of this was preparing. So now the actual work starts. So we create a context manager, a multiprocessing pool, okay, of the given pool size. So as usual, it's a good idea to use a context manager because after the work is done, it's pretty clear as soon as the pool is not needed anymore, these workers need to be decommissioned. They need to be destroyed, and that's done automatically by the context manager as soon as the code leaves the context that way. And if something goes wrong, the same happens. The context manager is going to take care of tearing down the scaffolding. Okay, then we use the map method, and as you can see, basically we have our count chunk function. That's the one which we defined on the previous slide, and we have the arguments. And the arguments, again, is a list. So basically, this is going to be distributed over all the workers. So each worker gets a chunk to do. Okay, so in this particular case, I had as many chunks as there are workers in the pool. So the length of the list, in this case, is equal to the pool size. That need not be the case. So I can have, for instance, 4 workers in my pool and have a list of arguments of a much longer length. In that case, it's quite simple. As soon as some work is done by a worker, it will get new work until that list at the end of the day is exhausted. So in that respect, it's quite easy to do. How this is divided, this work, is internal to map. So it might be that there's some kind of round robin going on. It might be a different partitioning of the work over the workers. You don't have any control over that, so basically, yeah, just hope that Python's doing the right thing here. And yeah, at this level of programming, yeah, we don't care that much, because if this starts to matter, then maybe multiprocessing is not for you, but okay. And then afterwards, of course, we have to collect things. So counters is going to be an iterable that contains all the results. In this case, it will be an iterable that has dictionaries. So basically, I can iterate over them, and then I just add the results together. That happens there. Okay, so parallelizing was really, really simple. We just had to write a function to do the work. We create the context, and that's it. One thing to remember, this with multiprocessing pool thing is, of course, a pretty expensive operation, because that's spawning multiple processes. As I already mentioned, essentially, such a process is a running Python interpreter that copies quite a bit of the state of the current interpreter into those workers. So yeah, this is expensive. So that means that if the parallelization here, or the time it takes to execute this map, if that is very low, then of course you're not going to offset that. It's absolutely impossible. If you have multiple operations which you want to do in parallel, then maybe it's a good idea to create the context and leave it open until you're done doing any parallel work. Because basically then the members in your pool, the workers, keep on existing and just get new work. So that is then, of course, the better approach. Don't do every parallel step in its own context manager, in its own with statement, unless you have an excellent reason to do that. Okay. So basically, this I've already told you.
There's a question.
A question in the chat. Thank you. Yeah, so the function itself, this function here, so what's its name? Count nucleotides, that's executed in the main Python interpreter. So basically in the Python interpreter where you start your script. So that's executed only once. The function which is executed multiple times is this count chunk function. And that is going to be executed in the workers. So basically in separate Python interpreters and running on different cores of your CPU. That's basically the idea. Yeah, so basically, if you have 4 workers, your pool size is 4, then in total you will have 5 Python interpreters running. The original one, and then 1 per spawned worker. So basically, in total, you will get 5 of them. That's the idea. Okay. Yeah, so if the question is because the question can go in 2 directions, so let me also make sure that I really answer the question. So it's not the case that the interpreter which is running the wrapper script, so this script here, would be executing anything which is delegated to the workers. So that's not the case. It's not somehow reused as a member of the pool. It's a separate interpreter. Okay. So how does this scale? Let's have a look. As you can see, it's not too bad. We get almost 2 as a speed up with 2 processes, and with 8 we get up to something like 6. So basically you get a decent speed up. It's of course not perfect. The parallel efficiency is not really brilliant. That can have several reasons. One reason in this case is, of course, yeah, this is I/O bound. So basically, I'm putting quite a bit of stress on my disk. So yeah, that should flatten out at some point. And you see that here, basically, when you go beyond 8 processes, things start to even slow down a little bit. So in total, for 1 billion nucleotides, you get 21 seconds as the execution time. So, yeah, seems good. Happy? No, sort of. Okay, let's put that into perspective. A small C application, really simple, no parallelization, actually sits here with respect to speed up. So a single core C application beats whatever you can do with parallelization in Python for this particular problem. Just as a reminder that Python is not your fastest language. Let's put it that way. Okay, now of course, the C implementation is naive, the Python implementation is naive, everything is naive here, so essentially it's just a comparison between 2 naive methods, not necessarily the best ways to go about this. Okay, so we saw the map method. What else can we do? What other kinds of processing can we consider? So you can send a job to a single worker, and then of course you would have more of such statements using apply. So each time you do an apply, basically you call a function with a single argument, and that is also blocking. So that basically means the apply method is not going to return while the computation happens. That's what blocking means. Okay, so it's much more interesting to use apply async, because that is non-blocking. So basically that means your function is going to be executed, and meanwhile the code that calls it continues. So this returns immediately, but that of course means that you can't use the result yet, because the result isn't there. The computation is going on, but you don't have the result yet. So that's the difference between blocking and asynchronous. How to handle asynchronous results we'll see in a minute. Then you have a map and IMAP. So basically apply a function on each of an iterable. And again, this is blocking. So basically that means, let me go back to the previous slide because there I can illustrate it easily. So basically, as long as at least one worker is still busy, that is not going to return. So basically, this script will be stuck on the line where pull map is called until all the work is done. That may or may not be what you want. And that's why, if you don't want that, there's also map async. So similar semantics, except this is non-blocking. Okay, there is also star map and star map async. So basically, the arguments are in fact iterable in that case. So it's a bit of a convenience function. It automatically does a star on the packed arguments. So yeah, it's a bit more convenient to use that. At some point, I should rewrite the example which I gave with the nucleotides in terms of a star map, because actually it makes programming a little easier. But okay. And again, the blocking and the non-blocking forms of that. So that means that, for instance, with an apply async, I can call a certain function having one worker do that, calling another function with apply async, having another worker do that, etc., etc. So basically, your apply and apply async make sure that you can give different workloads, different in the sense of not the same computation on different arguments, but a completely different computation to each worker. That's basically the idea of apply and apply async, while map is more like, okay, the same function is applied to many different arguments. That's the idea. All right, so results. As I mentioned, if you use async, then of course your function map async or apply async will return immediately, but that means that its return value is not going to be the actual result. Can't be, because it's not there. So what you get in a way is sort of a promise that you will get a result as soon as the work is actually done. And that is wrapped into an async result object. So async result is the type of what you get back from a apply async or as a map async. Okay. So you can do several things with such an object. You can wait, which basically means, okay, this function will block until the result is ready, and only then it will return. So if you would do something like map async and assign that to result, for instance, and then immediately after that result wait, that would be exactly the same as just doing a map without async. Okay, so you have the get, and that is going to block until the result is ready. So that is basically a combination of a wait and then retrieving the result as soon as it's there. What you can do is add an optional timeout value, which can sometimes be convenient. Suppose that you have an algorithm that potentially goes into an infinite loop, or which goes into some optimization which takes too long or whatever, then you can make sure that it's cut short at a certain point in time. So that's an option. In scientific programming, maybe not that useful. In general programming, quite interesting. For instance, think of a web crawler. Okay, you just have a bunch of addresses. If an address takes too long to reply. So basically, the web server takes too long to reply. Okay, just ignore it. You don't mind missing that information. You mind much more that one of your workers is stuck in something that just takes too long. So that would be a more real-world example of using these timeouts. It can be useful in scientific computing, but yeah, marginally so. Okay. Then you also have ready. So basically, that is a function which returns true when the result is ready. This is interesting because basically that allows me to do work. If I put this in a while loop, I can do work in my main interpreter while I'm waiting for the result. So I just do while not result ready, do some work in my interpreter. As soon as that's done, I can then get the result from the worker. Okay, then successful. So basically, that means the result is ready, and also there were no exceptions while it was executed. So basically, this allows you to overlap work in workers and the calling Python script. Because one of the things I could do, for instance, is the while not ready or while not successful, which is a bit dangerous, but I would use while not ready, that's more solid. What you can also do, of course, is say, okay, I have an apply async, I have another apply async, I have yet another apply async, and then I wait for all of them. So that is also an interesting use case for wait. Okay, so that's quite nice, all of this, but it leaves me with an annoying feeling or an annoyed feeling. Why? Because, yeah, what happens with data? How do I access data? Because actually that's going to be copied to a different process that is a copy, which means it needs memory. That is a copy, which means it takes time to make. So, okay, if I do this on large data sets, I might rapidly get very unhappy due to on the one hand, memory consumption, which suddenly is at least twice as large, and of course also performance, because all that copying data around is going to be expensive. So, what do we do? Back in the old days, nothing, live with it. Nowadays, there is actually shared memory. So the interface to multiprocessing I've shown you right up to this point is straightforward, easy to use, and so on. But under the hood, you have a different API as well, which is a bit more low level and, of course, a little bit harder to use, but that you need to use if you want to use shared memory. What does shared memory mean? Basically, the processes can access one another's memory, and they can access the memory of the original process, the original Python interpreter that is running. So basically, that means that no copying is required. Of course, good bookkeeping is required, because if you write to some shared memory location, you'd have to make sure that you don't overwrite one another's data. And this opens up, of course, the possibility of creating race conditions. Okay, so what can processes share? Well, basically, they can share a single value. So that's just a Python object at the end of the day. They can share an array, and they can also share a singularized FIFO queue. So basically, that's the first in, first out queue. And that's something that you might say, okay, what, why? Well, basically, this is a very useful construct if you are in a situation where you have work that gets produced dynamically. Because then you place that in a queue, and workers just monitor that queue, and they can take data out of the queue to process, and they can potentially put data into the queue again that needs to be processed. So a FIFO queue typically is a very nice construct for parallel programming at a, well, not so high level, let's put it that way. It's something that in scientific computing is still interesting, that you would hope not to have to use, but okay. For instance, to avoid recursion, this is a very nice way to do that. Anyway, so these are the things which you can share between processes. So if you have a non-atomic update operation, you should lock it. And an operation that's not atomic should lock. What do I mean by that? And what is an atomic operation? Well, the problem is that if you, do I have a slide of that? It would be so useful. No, I don't. Okay, should add such a slide. Okay, that's something that I do have slides about when I really talk about parallel programming in C, C++, and Fortran, but I don't have it here. I should add it. So basically, what does that mean? An atomic operation, and what is an example of a non-atomic operation? Well, let's take a very concrete example. I've got two workers, and I've got a value. And that value is simple. It's just a stupid integer. Okay. So the workers do some stuff, and as part of that, they change the value. It's simply incremented by 1. That's the only thing they do. So the value is essentially just a counter, a global counter. Okay. So that sounds really, really innocent. It's one operation they do, essentially just adding 1 to a number. Easy. Problems? No. Why would we have problems? Yeah, we have problems. Okay, why? Because that sounds weird that you would have a problem. Well, the problem essentially could be, depending on how you do this, if you do it very naive way, then the problem is that you are doing something that is not atomic. You might think, okay, adding 1 is single operation, easy. Yeah, not quite. Because this is not atomic in the sense that the first thing that happens is that you retrieve the current value. Okay. Then you compute the new value. Okay. And then you store the new value. These are 3 things, not 1 thing. So this is not atomic. Yeah, okay, so, yeah. So what? I mean, it could go wrong. Well, okay. Consider the following scenario. I've got 2 workers, and each of them, more or less at the same time, are going to increment that variable. Fine. The first one gets the value. Okay. The second one gets the value. They get the same values. Nothing changed yet. Okay. The first one adds 1 to it. The second one adds 1 to it. Okay. One of them is going to write. The other is going to write. And each of them is going to write the previous value plus 1. Which basically means 1 off. Because this should not have happened. So that's a race condition, because it depends on the order on the timing of certain operations. When would it have been all right? Again, first process gets the value. computes the new value, stores the value. Counter is counter plus 1 now. Okay. Second process gets the value, which is now counter plus 1, adds 1, value is counter plus 2, stores it. We have counter plus 2, everything's fine. But if these operations overlap, then you have a race condition and then you have a problem. Because the end result of that scenario is going to be counter plus 1 rather than counter plus 2. So that's something that is always a concern in parallel programming, in shared memory parallel programming. So basically, it's something that you have to be aware of. So what should I do? What I have to do is process number, the first worker is going to lock the value. Okay. Then is going to get the value, compute a new value, add the, store the value, and unlock it again. Okay. So now, suppose that we have the same scenario. Worker 1 gets the value. Worker 2 now also wants the value. It wants to do the same operation. So the first thing it now tries to do is to get a lock. It can't get a lock because the first process has the lock. So basically it has to wait, and it will wait until it can lock the value, do its stuff, and unlock it again. So basically that means this operation is now safe because while an object is being updated, while the counter is being updated, no other process can actually access that value. So nothing can go wrong. Yeah. Except that now we get to a second problem in parallel computing, which is potential deadlock. Okay. Suppose that I forget to unlock. There is somewhere a complicated if, and in some circumstances, yeah, the lock is not released. Yeah, then you see that you have a problem. Process 1 is going to lock. It's going to update the value. It forgets to unlock. Process 2 tries to take the lock, can't, because it's still locked, blocks until the process 1 unlocks, which is not going to happen. So basically it's stuck and it's just sitting there doing nothing, and you have a deadlock. This is a very simple case. That typically doesn't happen. Now, when does it typically do happen? I've got two objects and I have to update both. And then depending on the order, I can create a situation in which in which worker 1 has a lock on an object, A, tries to get a lock on an object, B, while worker 2 has a lock on B and tries to get a lock on A. Worker 1 is not going to release the lock on A until it has updated B. Worker 2 is not going to release the lock because it's waiting for A to release, for the worker 1 to release. So they both wait on one another. None is going to release the lock because the conditions are never going to get met in order to release their locks. So that is somewhat more, well, the more common case where you have a deadlock. So that is dangerous because, of course, that is a bug. That's a very annoying bug and something that you should avoid. So yeah, those are the basic problems which you face in parallel programming. On the one hand, race conditions. On the other hand, deadlocks. You have that in OpenMP as well. The risk on race conditions is definitely there. Risk on deadlocks typically a bit less because normally you don't need locking. But okay, if you do, then you can deadlock. It's also there for MPI, both deadlock and race conditions can happen unless you're a bit careful. So this is basic fact of life if you're doing parallel programming in any capacity. Okay, so basically that means let's get another example with now indeed a value. So we are going to assume that this p sum exists. This is just a function again which does the work. This is going to be executed by a worker, and p sum exists, and it is such a value object. So one of the things we can share. What are we doing here? We are computing pi in a really stupid way by throwing a dart at a board which is squared. But there is a circle thrown in the board, and basically if you hit the circle, you count it as 1. If you miss, it's in the board but outside of the circle, you don't count it. And then if you get a ratio and you multiply by 4, because it's just a quarter of the board here, then basically you get a value for pi. It's a very stupid way of getting pi, but okay, it's always nice to illustrate some parallel programming. Anyway, so basically each of my workers will do a number of tries, and of course these are independent, so no problem. The number of hits is initially 0. The dart is thrown, so x and y are coordinates somewhere on my square board, and if they fall into the circle, then I increment number of hits by 1. Number of hits is a local variable, nobody cares. Up to this point, no problem. But now, of course, I want to update the total number of hits, and that's our p sum. So basically, I can do that by adding number of hits divided by number of tries times 4 to the pi sum value. But as I already mentioned, this is not an atomic operation. I get the value, I compute something, and I store the value. So not atomic, hence I have to log. And this is very nice that we are programming in Python, again, because we have a context manager. And this context manager will take care that as soon as the body of the context of the with statement is done, that the log is going to get released. So that's nice. If you're programming in a programming language that doesn't have the concept of context managers, you have to explicitly unlock after you've done your update. So this diminishes, but doesn't, of course, eliminate the possibility of deadlock. Okay, so you can sort of view this p sum as a global variable. It's a location in memory where each process can actually have access to read it or to write it. Okay. To read it, if no one updates it, of course, you don't have to do anything special. You don't need to log, because reading is not an issue. This you can do concurrently without any limitation. If it gets updated, then of course you need to log. Okay, so how do we use the thing? Okay, so now we have to use an interface which is a bit more annoying. So this pool thing, which we could use in the previous example, now doesn't work because we need explicit processes here. Okay, it's not that bad. So again, we have a number of tries as a variable. The pool size is given, and then we compute the number of tries for each process, again trivially by having the total number of tries divided by the pool size. Okay, again we assume that this divides correctly, so basically this should be a proper integer. Okay, then we create a context. So basically we have a fork server here, and that basically means that we are talking processes. So when creating a context, you have a choice whether you parallelize using threads or processes. If I select fork server, I've got processes, and that's indeed what I want. Okay, so that gives me the context, and then in that context, I can create a value. This you recognize from yesterday. The string D means it's double precision value. Same typing convention as we have seen a couple of times. And an initial value, which is equal to 0. Okay, so this is going to be my shared variable. Now I've got processes. So as you can see, I create as many processes as I have in my pool size. I get a list of processes using this list comprehension. So I create a new process. The target is partial pi. Partial pi was my function on the previous slide, so that's the work I'm going to do. And I also specify the arguments, so that is the number of tries and my shared variable. Okay. So this creates processes, but that's it. It doesn't start them. So at this point, nothing is happening. Okay, so the next step is a for loop, and as you can see, it starts all the processes one by one in that list of processes which I just created. Okay, so now when that for loop is done, all the workers are going to process. That's great. And then, of course, at some point I have to make sure that things end, that I can resume my computation safely, that I can access the final value of p sum. So basically, I start the thread, I start the process, sorry, and then I join a thread. So basically, as soon as, that's not quite correct what I'm saying, so I have to be a bit careful. So basically, if I do process join, that is going to wait until that process is done. So doing that in a for loop means I'm going to wait until the first process is done. As soon as that happens, I'm going to wait until the second process is done, the third, etc., etc. Now, if everything happens in parallel and we don't have any weird load balancing issues, then of course, process 1, 2, 3, etc. will finish approximately at the same time, and this for loop will just continue without any issues. If you do have load balancing issues, then of course with this you need to be quite a bit more careful. But anyway, and then of course we can safely access the value of p sum, because now all computations have been done. Each process has in turn updated its p value, and we are good to go. Yeah, question.
In this case,
yeah,
you only create one process.
So in this case, do we only create one process? No, you create pool-sized processes, because that happens in that list comprehension here. See, this CTX process means I'm creating a new process in the given context. So you can view the context sort of as a process pool. It's sort of a pool. It's not a pool. A pool is a wrapper around the context, but it plays the role of a pool. And I'm creating processes one by one, and I'm creating pool size of them. So I will have, context will have pool size processes. The default indeed happens to be 1, but yeah, I call this with whatever pool size I want, of course. It's just that I showed the default to be 1. So I have indeed in my context as many processes as I choose to have, basically my pool size. So in scientific computing, your pool size should definitely not be larger than the number of cores you have on your CPU. If I have whatever number of cores, 32 for instance, then my pool size should not be more than that. Because otherwise, workers will start to share a core, and then of course all hell is loose. Basically, they will lose cache, they will lose time, context switching, etc., etc. So that's a situation you don't want to be in. You are not safeguarded against this, because in more general programming, it may be beneficial to have more processes than you have cores. For instance, again, let's take the example of a web scraper. The main bottleneck there, the main performance bottleneck is I/O, the network request and the response of the server, and of course the network bandwidth of whatever is in between. So basically that means that in that case, workers spend most of their time just waiting for a request to be fulfilled. And that is totally unpredictable when that will happen. Because yeah, you don't know how fast some remote web server is going to respond. So what do I know? So basically, given that workers will spend most of their time waiting, it's much better to have more workers than you have cores. Because it doesn't matter that they share a core, because they can happily share a core while they're waiting anyway. That doesn't cost me anything. That's the case for that type of use case, but that is very rarely the case for scientific computing. So don't oversubscribe. With oversubscribing, I mean the number of workers should not exceed if the number of workers exceeds the number of cores you're oversubscribing, don't do that. In scientific programming, typically bad idea. Okay. Let me perhaps, because I don't think I have a slide on it, go back one step, because aren't we making this a bit too complicated? I mean, in fact, if I look at this function, why do I have the local variable number of hits here? I could just use psum and update that, and I would get the same result, right? My program would be correct. My program would not deadlock. So correctness is fine. But what's the problem if I were to do that? Yeah, no. I thought there was an answer, but why am I overcomplicating things? Okay, reason. There are several reasons. One reason is overhead. So basically, locking is, again, an operation that takes time. You need to synchronize, and also you need to check, etc. So basically, it's something that potentially generates overhead. So if I do that in a hot loop, so basically in a loop in which there is not much to do, because creating two random numbers and computing a few numbers and comparing them is really, really cheap. So that's a loop which iterates very, very fast. If I have this operation here with psum dot get log and then psum plus equals 1, yeah, well, that is going to generate quite a lot of overhead. Another thing is I have very many moments that the variable should be locked. Okay, now imagine I have many processes. So if I would do it in the for loop, the locking, then almost always a thread would have to wait for another thread. A process would have to wait for another process to unlock, because the probability that your variable is going to be locked is really, really high. And that happens in a hot loop, so your performance would be abysmal. Okay, so why is this way less of a problem now? Well, the payload of my function is here, outside of the update of the shared variable. So I will have at most as many log operations as I've got workers, no more than that. In the other case, I would of course have p tries, wait, is it p tries? Number tries times the number of workers log operations. And that's of course several orders of magnitude more, because my number of tries is a million, whatever. So basically I would get like potentially 4 million logging operations. Now in this case, as the code is now, I only have 4 logging operations if my pool size is full. And even if they manage to really try to lock this variable at the exact same time, even then it doesn't matter, because that update operation is going to be very fast. So yeah, it might be that one worker needs to wait for another, but that waiting period will be very short anyway. So that makes this way more performant. And I'm not sure whether I probably don't have the code. I should add it just by way of experiment. How much worse would it be if I were to do the locking in a, let's say, not so smart way? So basically within the hot for loop. So that's something to take into account. If you have a shared object, whatever it is, your array, your value, whatever, and you need to lock it, yeah, try to avoid doing that in a hot loop, because that is going to be disastrous for performance. Okay. So this approach here, okay, I need to move the slide a little bit below. Basically, this approach with processes start, processes join, this interface looks quite a lot like the threading module. There you would do the exact same thing. Those of you who have ever programmed multi-threading using pthreads in C or C++, this is the exact interface. You start a thread and you join it, which will happen as soon as it's completed, as it has completed executing. So that's essentially the idea. So where the green line is, essentially, you've got your parallel programming, your parallel processing. Okay. So you've got these arrays, you've got this value, but yeah, we don't want to use these data types typically. Why would we create a new array? Is this array as performant as our NumPy arrays? I mean, so the answer to both is no, we shouldn't, and no, it won't. So basically, it would be much nicer to somehow be able to use NumPy arrays as shared stuff. Okay, and that is possible if your version of Python is recent enough. But as you can see, it was used in Python 3.8, so yeah, well, probably you have something more recent. Okay, so basically, you can actually share chunks of bytes now. Oh, chunks of bytes, that reminds us of something. That reminds us of the buffer protocol. Remember from yesterday? Okay, so here it is again. So the buffer protocol is again going to be quite valuable. And remember what supported the buffer protocol? Indeed, NumPy arrays. Great. So basically, we can actually use a shared memory manager. So that is going to take care of allocation of shared memory and deallocation. You don't do that automatically. And it will work also as a context manager. So shared memory is then just a sequence of bytes, and it, as I already mentioned, it interoperates with anything. that supports the buffer protocol. And of course, the thing we are mostly interested in are NumPy arrays. Okay, great. So how does this work? Well, okay. Again, we need something, and that is the shared memory manager. And as you can see, that is again with a context manager. That's pretty great because when we leave the context, when the execution leaves the context, all the memory managed by the shared memory manager will be released automatically. We don't have to do that. The context manager will take care of it. So again, that's something that's pretty neat in Python, that you have this concept of context managers. Okay, so in that shared memory manager, we create a pool, and don't ever swap the two. So you really first need your shared memory manager and then the pool, not vice versa. So basically, you create a pool with a given pool size, and then we create a size thing here. So basically, we compute the size of a complex number. We get the item size, etc. So this is just to get the number of bytes which is taken by a single complex number in a NumPy array. And then we create, using the shared memory manager, we create shared memory of a given size. And that is basically the size of an individual complex number times the array size I want. Okay, and then I create an ND array. So now I'm just in NumPy. Okay, and this is perhaps a little bit weird. You've likely not seen this before. But what I'm doing now is I'm creating an array which is not initialized, but which has a certain size. It has a certain D type, and I specify a buffer. So basically, I'm going to say to NumPy, use this chunk of memory, which I'm now passing to you, to store the elements. So of course, this buffer must have sufficient size to store size elements with a given type. But that's okay, everything is consistent here. Because I computed the size of an individual array element, and for the buffer size, I multiply that by the number of elements in my array. So all of that is consistent. So I get the buffer out of the shared memory, which I created using the shared memory manager. So this buff attribute is the address, let's say, of the buffer that can be used to store this array. Okay. And then my Z buffer is just an ordinary NumPy array. The only thing I've done is make sure where its data is stored. That's what I've specified using this optional buffer attribute. So anything I can do with a NumPy array, I can do with such an ND array, which I created in that way. Okay. And then I do some computation here, basically init Z, number of points, and then more stuff happens, etc., etc. Okay, so this shows us how to use such a buffer. Okay. Again, the order really matters. Don't swap the two because then it doesn't work. Okay. So how do we do this now? Well, basically, what we have is we've got some shared memory here. Okay. And those are arguments. And as you can see, I'm using a list comprehension in order to create some arguments. So my arguments are a tuple, stored in a tuple as usual. I've got Z shared memory. I've got N shared memory. And probably you're guessing where we're going. Indeed, this is again our Julia set. So Z is going to be our complex domain, and is going to be the number of iterations for each complex number in that domain. Okay, and then there are some parameters. So I times work size, minimum of something something. So that's basically to make sure that the worker will know which part of this array to process. Compare that to the chunk size and the file position which we had in our nucleotide counting example. Okay, so we have a counter, and we have PID. So basically in our pool we do an IMAP unordered, and we compute partial Julia with arguments. Okay, this unordered is it's useful to have because it says, well, okay, it doesn't matter in which order you do these computations. And given that we already know that we have problems with load balancing in the Julia set computation, some complex numbers take longer to iterate than others. Basically, that means that if the parallel processing framework knows that it need not do things in order, it can much more easily shuffle work around and basically ensure that we get better load balancing. So if I wouldn't use unordered, the result would be correct, but performance would be less. I don't know whether I have a comparison, but it's easy to check. So the unordered is in this case good for load balancing. And of course, I do know that I can do these computations in any order because it doesn't matter. It's computations on individual complex numbers. So the order is irrelevant anyway. Yeah.
I don't really get it. If you did pool.map, would it order it, but then isn't the fact that the process is gone, like the parallelization?
No. So basically the question is with map, what would it do? Well, basically what it would do with the map is it would say we have, for convenience, we have 4 workers. Okay, my pool size is 4. So it would assign the first argument to worker 1, the second argument to worker 2, the third argument to worker 3, the fourth argument to worker 4. Okay, one of them is done. It gets argument 5. Another one is done. It gets argument 6. Here, it can get anything. So you've got much more freedom.
Okay.
That's the idea. Compare that a little bit to when we talk about p-range in Cython. I said, well, okay, you have these OpenMP schedules. With static, you had dynamic, you had guided, and so on. So this allows you to. It's the similar idea here.
So your list is basically longer than your pool
Yeah.
size.
Yeah, exactly.
Okay,
Yeah. Okay. So basically, PID counter. Why do I do that? I don't remember why I need PID counter, to be honest. Yeah, no, I do. Now I do remember. Basically, that's just to see which worker does how much work. That's essentially the idea. So the counter actually just checks how who does what. So this I is going to be the IMAP is going to give me a process ID. So that's why I use the IMAP here. Okay, so basically, this is now, of course, my Julia function itself. So this is going to be executed by each worker. So each worker just does the same thing, but based on different arguments. And of course, the differentiation is, of course, index begin and index end. So basically, that means that each worker knows which part of the array it will operate on. So I've made sure that I can actually now write to my shared memory without any conflicts and without locking, unless I've messed up. But okay, let's assume that there are no bugs here. So in that case, this is lock free. I don't need to lock. Okay, because I'm going to write indeed to shared memory, but in different locations. So each worker is going to write in its own location. So I can't have this race condition. That's just by the way I program, in this case, not possible. And of course, that's nice because no locking means no overhead, no potential deadlock, and so on. The drawback is, of course, that if I messed up and I miscalculated this index begin and this index end, then, of course, processes will overwrite one another's data, and I'm going to be somewhat unhappy because that's a bug. So yeah, that's the drawback. I have to be careful. Okay, so basically, what are we doing now? Essentially, we have our array, and again, it is an ND array of NumPy, and I'm going to set a size, and that's just going to be the difference between the last index and the first index. We're using Python semantics where the end index is not included. Okay, again we have ND complex, and then we have the then I use the Z shared memory buffer in order to create a view on that data. And as you can see, I use a slice here. So basically, I only expose that part of the shared memory that this worker, for this particular work item, should operate on. So I do that for Z, and I do that for N. So this is actually just the same, only on two different arrays. Okay, once that's done, I can just treat Z array and N as I did before. So this part of the code is the exact same as before. Okay. And then I also return the PID. So basically, that allows me to do some counting. This is just for illustration purposes. So basically to see how many work items were done by a certain process. Because the process ID is going to remain the same as long as the worker lives. Okay, so basically that's the ID here. How well does it scale? So basically you end up with 71% efficiency on, again, 36 cores in this case. So that is comparable, I think, to what we had with the other approaches which we did with respect to parallel efficiency. So it's reasonable. It's not stellar, but again, just as I explained yesterday, the Julia set is annoying to compute because you do have load imbalance, and compensating for that is non-trivial. So this is not bad, especially since we're at 36 cores. So basically, that is quite a bit of parallelization here. Okay, so this is actually cute. This starts to resemble, let's say, OpenMP without convenience. So yeah. With some luck, next year or the year thereafter, I can talk about OpenMP in Python when this goes into something that I would consider stable enough to do some decent working. Okay. There is a remark. Let me see. Little workers have trouble with the GIL. That depends on what you pass as arguments. So basically, that's something that you have to be a little bit careful with. If you pass an object as an argument, and each worker gets the same object, you have a problem. Because then indeed, the GIL starts applying. So in that case, you better work with a shared variable where you don't have any trouble with the GIL. Because shared variables are exactly there in order to avoid the whole issue. So just passing in an arbitrary object might be a problem. What you can do is passing in copies of an object. Do you want to do that? I don't know. I mean, if it's a big object, nah, probably not. If it's a small object, well, I don't care. But at any rate, if you pass in a copy, make sure to pass in a deep copy. I mean, if it's a structured object and you just copy it, the things it refers to internally will not be copied, and you have still a GIL issue. So with a deep copy, of course, you don't. But then, yeah, you have a copy. So do you want that? I don't know. Again, it depends on the size of the object, how often you need to do that, and these kind of things. But basically, yeah, that's a very good use case for shared variables, or shared memory in general. Okay. And of course, if you just read it, you don't need to log, so then it's rather cheap. I hope that kind of answered the question of mine.
I think that was a question. I think that was an answer for when you asked why am I visualizing.
Okay. A question I didn't answer then. Okay, whatever. Let's assume it's solved. Okay, so multiprocessing is nice and probably the most useful. Yeah, okay. So there is an alternative, which is futures, but yeah, in a way, we might want to skip that because it's similar to multiprocessing. It's a bit easier to use, but the drawback is there is no shared memory. So, yeah, I'm not really convinced how useful this is. This was essentially an attempt, I think, to create something a bit more modern than multiprocessing. But then they didn't go all the way, so this is useful, but much less so for scientific computing, in my opinion. But okay. The point is, the difference is that it's always asynchronous. So basically, you have never blocking calls. Okay, you have some blocking calls, but that's the idea. So it also works in a context where you would use other asynchronous computing. You have a thread pool executor and a process pool executor. You can already guess what is what. And basically, simply three methods: submit. So that's like apply async. You have map. That's like map async. And you've got shutdown. Yeah, which shuts down. Easy. Which you don't need to call if you use a context manager, but okay. So basically that's it. So a very simple interface, and it's always non-blocking, always asynchronous. Okay, so if you use map, set the chunk size to something sensible because the default is 1. That's the same remark as with a dynamic schedule in OpenMP, because also there the chunk size is often 1, which means that you get quite a lot of overhead. So this is actually the same reasoning here. Set the chunk size to something that makes sense. Okay, so just like a result object which you got from async calls in multiprocessing, every call in futures is going to give you a future. So basically a promise that something is going to happen. So basically, the object which you get is a future. You can get a result, So that's similar to the get in async result. So basically, it will wait until the result is there and then continue. Done, yeah, true when done. So that's similar to ready in multiprocessing. And then running is true, basically when it is still computing and it cannot be cancelled. And then you have cancel, which is an attempt to cancel the computation. So this is something that you can do with futures, which as far as I know you can't do with multiprocessing. So basically with multiprocessing, there isn't the option to, while the task is running, try to get rid of it. Okay. Again, in scientific computing, there are use cases, but yeah, not that many. And then cancelled is true when you successfully cancelled a computation. So let's do pi again. It's very similar, of course. So in this case, it's just going to return the local computation, easy. And then here we have an environment, sorry, a context with a pool, in this case an executor. We create the arguments, we use a map, and we sum the results, and basically that's going to be it. Okay, so implicitly here there is a get because I'm using results, so it has to wait up to that point. So it's a bit simpler in a way than multiprocessing, but yeah, it's not as useful in a scientific context due to lack of shared memory. Any questions for this? Okay. All right, so in concluding, if you can use multi-threading of underlying libraries, it's definitely a good idea to do that. That is for free. And of course you can combine in the sense that you can use multi-threading at the level of your library and using multiprocessing to parallelize that. If you do that, you have, of course, to take a bit of care, because suppose that I have a node with 69, for instance, a Sapphire Rapid node, and I run 4 Python processes with using multiprocessing, and each of them uses NumPy. None of them takes care. What is going to happen? Okay. A NumPy call is going to be executed. Under the hood, a BLAS library that parallelizes it, be it OpenBLAS or MKL, is going to check, okay, how many cores do I have available? Ah, nice, 96. Great. So that computation is going to be done with 96, using 96 threads, expecting 96 cores. Okay, fine, nothing is wrong. But the second worker, the NumPy call, does the same thing. It's going to see 96 cores. Okay, so in total, there will be 96 times 4 processes. I'm not going to start computing how much that is, but that is at any rate quite a lot more than 96. So basically, threads are going to share cores, and I will get overhead, and my computation will dramatically slow down. So if you are in such a scenario, make sure that the OpenMP calls in the library know how many threads to use. And you can do that using environment variables. So OMP num threads, for instance, allows you to specify how many threads can be used by an OpenMP application or library, whatever. So in our example, OMP num threads should be set to 96 divided by 4, whatever that is, 27 or something, or 28 likely, I don't know, whatever. So basically that number. And then of course each worker has 96 divided by 4 threads. Total number of threads is 96, is equal to the number of cores, no problem, no oversubscription. But that's something to remember. Also, you need to be aware whether or not your Python application at some point uses multiple threads. Because you might not notice, unless you try, it's a bit, yeah, you have to be a bit careful there. Okay, remember, process creation is costly. That's always the case. That's even the case for thread creation, much less so, but still, it's an expensive operation. So basically that means that you would best leave a pool open as long as possible until you don't need to do any more processing. Because creating the pool is creating the processes, and if you do that very often, you get quite a lot of overhead aggregated. Okay, same with locking. So basically, yeah, try to lock as least as possible. Of course, don't forget to lock because if you need to, because otherwise you've got race conditions, and that's something that you definitely want to avoid. If you lock multiple objects, make sure that if multiple threads do that, that you don't get into that deadlock situation which I described. Then I would say for fine-grained parallelism, so parallelism where there is a lot of communication required, a lot of synchronization required, lots in terms of per second or per unit of time, this is not going to work very well. So this is going to work for things that can happen in parallel for quite a long time, seconds, hours, not less than that. Basically, without needing synchronization between processes. You can do it. If you do it right, overhead will not be too bad, but typically, yeah, this is not written for that. And then, of course, you have to remember that all of this is limited to a single computer. That's fairly obvious, of course. Okay. Any questions about this part? Okay, then I think, yeah, it's time for a break. And my timing is excellent because it's just exactly the same time as yesterday, which is pure coincidence, but I can always pretend that it's sheer planning. Anyway, let's break till 11. And if there are questions, feel free to put them in the chat or ask them. Okay.
for the certificate?
It will be sent automatically. So the secretary's office will scan it directly. Well sent, will add to the something. It's one of the convenient things of organizing it via KU. Then I don't have to take care of the certificates because otherwise I have to do that.
Fair enough. You just add them to a list and send it over to the secretary.
Sorry?
You just add the names to a list and send it to a secretary.
Yeah, and it's already in that system. Right. So they have a list of participants, for them it's just a click of the button and the certificate rolls out. So it's very easy. If I have to do it, I have to start merging documents, printing them, etc., or creating them into PDFs, etc., etc. And
Okay.
it's unpleasant. Can you also open?
Yes. Is it tomorrow? It's here. Okay, thank you.
Okay, let's resume. All right. So we need to switch to the chat. And yeah, okay. So, any questions about parallel programming with Python? Not really. Okay. So another thing that is sometimes an issue is that your data set is in fact larger than you can store in the memory of your computer. And that is, of course, annoying. And there are several ways to deal with that. So for some problems, it's not so much of an issue because you can kind of load the part of the data which you need, process that, load another part of the data, process that, etc., etc. So in that case, it's not exactly disastrous. If that's not the case, if you really need to load all the data, then of course things get more interesting. And then one of the options which you have is to use more than one computer. Store part of the data on computer 1, the other part of the data on computer 2, and so on. So that brings us to distributed programming. And again, there are, for Python, several ways to do this. And one of those, which is conceptually rather simple, is Dask. And that's what we're going to start with. So basically, Dask can help for both cases. So out of core computations, out of core means my data is too large to store in RAM, out of core computations on a single computer, and doing computations on multiple computers. Either because you don't have enough memory on one, or because you want to split the processing over multiple compute nodes. Okay. So data sets can be very large for many reasons. It may be many files. It may be large files. Or it may be many large files. But essentially the idea is your entire data set is not going to fit in the RAM of your computer. That's the central idea here. Okay, so basically that's out of core computation in that case. So what are you going to do, or what is going to be done? The computation is actually going to be decomposed into a graph of subtasks. So a large task is going to be decomposed into a graph of subtasks. Okay, can we do that? Yeah, typically you can. For instance, consider a matrix-matrix multiplication with very large matrices. You can decompose that in many smaller matrix-matrix computations and then some aggregation, and you get the final result at the end of the day. So you can typically do that. Can you always do that efficiently? No. Your tasks must be large enough, and large enough in terms of compute time. So basically, it can't necessarily be done very efficiently, but typically you can get it done anyway. And for some tasks, it's really very efficient. So basically, your mileage may vary depending on what you do. And then, of course, if your original task is decomposed into a graph of subtasks, then of course you get something for free. To be precise, you see immediately which tasks can be done in parallel. Because if they don't share data, they can be done in parallel. And that's exactly the decomposition you've just done. So this decomposition gives you two things. It's division of your task in such a way that each subtask is going to fit in memory, and due to this decomposition, you also immediately know which tasks can be done in parallel. So easy. And such a graph is going to be a directed acyclic graph, a DAG, because yeah, I mean there can be cycles there. That's not an option. Okay. So essentially, this gives you both parallel and distributed memory at the same time. Okay. So basically, let's take an example. And I've got a data set, and my data is stored in CSV files. Okay, so there are timestamps plus 100 variables. So for each point in time, I've got a measurement of 100 variables. Whatever. They're random numbers, no one cares, but you see where this is going. Okay, and I've got 200,000 measurements per file. Okay, so yeah, that's pretty sizable. And I've 800 files in total. Okay, and the data spans a year, essentially. That's the idea. It's all made up, so no one cares, but that's the actual idea. Okay. The task is to compute averages for each variable and group by month. So it's a simple group by on the date followed by a sum per variable. Kind of easy, conceptually at least. Okay, so you can write a program that does that. I mean, it's fairly straightforward to write something like that, but of course, yeah, do you want to? Not necessarily to do it in a primitive way. So you would like to do this at a somewhat higher level because, yeah, grouping, etc., is a bit annoying. And of course, if you're familiar with pandas, this is really, really easy. As I just said, group by followed by a sum, and you're done. So yeah, it can hardly be easier than that. But the problem is, of course, that this is not going to fit in memory because the whole data set is 290 gigabytes. Okay, typical compute node only has 256 gigabytes of RAM. So yeah, even on an HPC compute node, you're kind of stuck. Yeah, I know large memory nodes, etc., but okay, I can make this 16,000 files. So I mean, it's just generating random numbers, so it's easy to get to a point where it's not feasible in the RAM of any computer. Just to keep things finite, this will do. Okay, so pandas is not an option. That is not going to work. I need something that's able to do out-of-core computations. Okay, so what I can do is use Dask. Dask is a Python framework for distributed computing and out-of-core computations. So I can import a Dask data frame as DD. If this reminds you of import pandas as PD, that is not really a coincidence. Because the first thing I'm going to do is to create such a Dask data frame. And I'm just using df like I would normally do in pandas. And I use the read CSV function, which also happens to exist in pandas. So yeah, it's a slightly different function in the sense that the implementation is different, but conceptually it does the same thing. And as you can see, you can do a bit more because I can specify a file pattern here, so a glob, rather than a single file. So remember, I had 800 of such files. So they, in the file names, have the format time series underscore and then some number .csv. Okay, and I also say, okay, the column which has timestamp as a title, this you should consider a date time. Do the conversion, please, for me. Then this is already a time column. Okay, so I read those CSV files. No, I don't. I only say that they should be read. I didn't ask Dask to do it. So what I'm doing now is I'm building a graph of tasks, which Dask internally is going to decompose into manageable chunks. So this statement will return almost immediately. It's not going to do any actual reading. Okay, then I have my data frame, so I can do a group by on date per month. So this would be identical to pandas. And I do a mean. Okay, I thought it was a sum. Apparently I do a mean, whatever. So basically, I get my values. But again, I don't. In the sense that I'm only declaring intent, I'm defining my tasks. Nothing is executed at this point. But then, of course, I do want something. So now my task graph is entirely specified. Okay, so I compute my result.compute, and that gives me an actual, that will do the computations. So two things are going to happen when I call compute. First, Dask is going to analyze my workflow. It's going to decompose it into subtasks, and then it starts to execute those subtasks in such a way that some can be done in parallel, while others have to wait until some tasks are done, etc. It's a DAG, so it's very easy to do that. And then I have an actual data frame which I can do something with, and I'm converting that to CSV for my results. And of course, the CSV file is not going to be large. That is just going to be 100 columns, 12 rows, that's it. One mean value per month. There are 12 months in this thing. So basically, it's just going to be a small CSV file. And also, of course, crucially, the result of the computation is going to be small. That fits easily in memory, it's trivial. Okay, so that was easy because there is not much different from your typical pandas code. The import is slightly different. And here I have this compute step. Apart from that, it's identical to the pandas equivalent. Okay, so basically, as I already said, the subtasks fit in RAM, and some can be done in parallel. Actually, many can be done in parallel, because if I'm computing mean values, then of course I can do that, for instance, file to file. It's easy. So there are many things which can be done in parallel here, and that is also going to happen. So these are the differences highlighted. As you can see, not that many. Okay, so that was not much effort. Let's see what we get as a result. Well, the first result is I can actually do this, which is already great. Now, I can, of course, also do this with pandas. I have to write some additional code. My pandas program will look differently, because what I think I did, I don't remember, is I computed it file by file and then aggregated the mean values, etc., etc. Okay, if there are not too many weird things going on, that should give you sort of the same result, not the exact same, but sort of the same result. But basically, I have to write some manual code in order, or manually some code in order to make sure that everything gets processed without me reading 290 gigabytes in RAM. You can do that. It's easy. The script is there. And as you can see, it takes 1 hour and 37 minutes in order to do the processing. This is a fairly old CPU, if memory serves. That would be Skylake, I think. Regardless. And of course, this is Pandas, so it runs on a single core. Okay. So with Dask, it takes 10 minutes. it uses the same CPUs, but in this case dual socket. So essentially, I will have in total, I'm not sure whether I use 20 cores or 2 times 20. I use 20 cores, let's put it that way. Because that machine has more cores, but I use only 20. Okay, so I get a 6 times speed up, so that gives me a fairly crappy parallel efficiency, because I use 20 cores rather than 1. I get a 6 times speed up, so my parallel efficiency is not exactly great. 30%. Now, if I need to do this only once, it's fine, I don't care. If I do this many times, then I should start thinking whether I can crank up that parallel efficiency a little bit, because 30 is really, really quite bad. But okay. Now, can I get better? Maybe. But one of the things to remember is, of course, that this is a problem which is I/O bound. Once I've got my data, the grouping and computing the mean values is a very short operation. So basically reading my data, and especially reading CSV files, is going to be my bottleneck. So this is, again, something that is more I/O bound than it is compute bound. So yeah, it's also memory bound, since once I've read stuff, again, I don't compute much. So it's mostly I/O bound, then memory bound, then compute bound. So improving this is, not so easy to do, because the task is so trivial. I mean, the computational load is very low in this case. Okay, so basically, indeed, I had forgotten how I implemented it, but it was indeed file by file. And then, of course, you have to do a group by more or less manually. Can be done, not so hard, but okay. Dask makes it a lot easier, so why not use it? And it gives me a very decent speed up, so there's no reason not to do that. Okay, so what can we do? Well, much of what we can do is which data structures, depends on which data structures that Dask supports. And it has support for quite a number of things. So basically for data frames, and that's of course very easy, because it compares one-to-one. It maps almost one-to-one on pandas. So if you have a data science problem in which you process pandas data frames, then transitioning that to Dask is really quite straightforward. It also has, yes, one thing I may want to say here, it actually has nothing to do with this particular training. There is a separate training that goes into much more details, but using CSV as a data format might not be your best choice. Reading CSV files is really slow. So that's something to keep in mind. If you can pick a different data format, such as Parquet or something like that, your I/O operations will go much faster. Just a side note. Anyway, so it also has support for arrays. So similar to the NumPy ND array, so multi-dimensional arrays. And those can be read, for instance, from HDF5 files. So that's also very convenient. Another data type it supports, it's a bag. So a bag essentially is a set with counting. So elements can occur multiple times, but order is not preserved. So it's sort of a list without order, if you like. Or it's a counter object which you find in the collections part, collections module of the standard Python library. And then it has also something delayed. So basically that means that's a way to actually create your own task graph. So you can create task graphs manually as well. And for that you need a delayed object. Okay, so which components do you have in order to get all this to run? Because yeah, you already see that that will require some infrastructure, software infrastructure. So Dask is pretty straightforward. It has a scheduler. So that is, of course, responsible for creating workers and managing tasks. And then a number of workers, which you can specify. Okay. And then there is a client. So basically, the client is your Python script. Your Python script is going to interact with the scheduler. And the scheduler interacts with the workers and sends information back to the client at the end of the day. So that's essentially how that works. So the task graph goes from the client to the scheduler. The tasks plus the required data go to the workers. The workers return the results. And of course, finally, the scheduler aggregates results and sends them back to the client. So that's how that works, pretty straightforward. And you can have workers wherever you want. So basically, I can have workers on multiple compute nodes. So that's nice because that means that I'm no longer bound to using a single compute node. I can run my script in such a way that it leverages as many compute nodes as I can potentially get my hands on. And that makes sense in the sense that I have a reasonable parallel efficiency. Okay, that was easy. So there's still the old script. Yeah, so this is basically for the old scheduler, not for Slurm. I should have an updated version of this. Let me check. Because I know I worked on it. I'm not entirely sure I finished it, but let's see. That would be in the task directory. And with some luck, there is a Slurm file here, which there are actually multiple. Why? Yeah, okay, I see. Yeah. Let's take the one for which we had the average of the CSV stuff. Okay, I'm not so sure that this I think is for the wait, what am I doing here? Because no, this doesn't set anything up. This is strange. Just a second. Because that just executes the script, and I would expect that I'm actually launching the. Yeah, this is a better example. Yeah, okay. This is the one I was looking for. And this is too small. So let's quit this. Let's increment the font size a bit so that you can actually decipher this. And let's show this. Okay. So what I need to do is I need to start my scheduler and I need to start my workers. So I start, of course, with the scheduler, and then I can start the workers. They connect to the scheduler, and that's how things work. And then I can run my actual payload. So then I can run my Python script. Okay. Now, if you think in terms of ordinary jobs, then of course what you specify is the number of tasks you want to run, the number of cores per task, the memory per task, etc., etc. So all these kind of parameters you set. But now, how are you going to do this? Because you've got three things going on here. One thing is the scheduler. The other number of things, because actually it's more than one, are workers, and they don't have the same requirements. So basically, the scheduler, as far as I'm concerned, can happily run on one core. I don't care. The workers may use multiple cores because they, under the hood, do some stuff which can be done in parallel. So yeah, how am I going to write my my directives for Slurm? Now, in Slurm, you have a mechanism to do this, and that's a heterogeneous job. So basically, your job consists of different parts that each have their own directives, their own specifications, and that's happening here. So as you can see, I've got this head group here and there. So that is specifying the different specifications. So of course, they all use the same account. That's pretty obvious. And why is there a PBS thing here? That seems pretty bad. So that should, of course, be as batch. So basically, I set the time, and the time is the same for all of them as well. Okay, then I specify the number of nodes, the tasks, and the CPU per task as 1. That's going to be my first group. That's going to be most likely my scheduler. Okay, then I have this head group marker. So this is going to be the second part of my heterogeneous job. It's going to run on the same cluster. It's going to use 2 nodes. It's going to use 2 tasks, and each task can use 72 cores. So this would be a job which I intend to run on our isolate nodes, because they have 72 cores each. Okay, and then I have a third group, again, that runs on WISE. That's the name of our cluster, by the way. So it runs on a single node, it's a single task, and a single CPU. That's going to be the group for my client. So I've got 3 groups, one for the scheduler, one for the workers, and one for the client. Okay, so basically, here I'm doing some preparations. So basically, I need the name of the node on which the scheduler is running. So I do host name. Then I prepare some stuff, compute the number of workers, etc., etc. I set a port. Just a hint: if you're on VSC infrastructure, use as a port number your VSC ID, because that's going to be unique. That's easy. Because if 2 jobs run with on the same port, on the same node, you're going to have a problem. Anyway, so let's scroll down a little bit. Then I'm going to, at some point, launch the scheduler. Which is happening here. So I'm doing that with srun, and I'm using the variables for the first job, which I don't have to do explicitly. Ew. This does not seem complete, because this should not be an SSH, this should be an srun. Okay, so I should actually launch my workers with srun rather than with SSH. So apparently I started working on the script and then forgot about it and didn't finish it. I do have one which is complete, but that is in a different training. Okay, I have to. I'll fix it in the repository later on. Apparently I got some work in progress and then got distracted and did something else. And then finally, I should have another srun for running my client, which is happening here. And the client, of course, needs to know about where to find the scheduler. So you need to pass the scheduler node and scheduler port number to that client. Similar for the worker, it also needs to know the scheduler node and the scheduler port, because the worker is going to contact the scheduler saying, okay, I'm here, please give me something to do. So that's basically the idea. And this is really, really incomplete. But I hope you see where this is going. I will update the Slurm script here, because That is something I apparently last year forgot to do. I'm going to make a note of that slide number so that this time, hopefully, I get around to do it. Especially since I already did the work, but that went into the training on workflows and not didn't propagate to this one. Anyway, don't do this, that's bad idea. So what does the client look like? Well, basically, you start a client, okay, and that needs the scheduling host and the scheduling port. Okay, so those somehow get into your client using ArcParse or whatever library you want to use. And from there on, nothing special happens anymore. Basically, the writing is going to happen once there is a client that is going to be used automatically. So yeah, that is quite straightforward. Okay, so this is the only thing which differs between doing this distributed or non-distributed. So non-distributed is just you do this on a single node. It's going to do the decomposition for out-of-core computations. If you want if you want to use different workers and so on, this is the way to do it. You just have to start a client, and that's essentially it. Well, start a client. No, that's not. Yeah, you create a client which will connect to the scheduler, etc. Okay, so that is quite easy. It also has an API, which is similar to the one which we already encountered with the futures. So basically, it has concurrent futures-like API. So basically, we can work this way. I have a Python function, a very complicated one, which computes the square of a number. Okay. So yeah, this is really a waste of time. This is just to show you how it works. So I create my client as usual, and then I do something similar as we did before. I do a map of square to data, and data is some list of numbers which I want to square. And that is going to give me a future, essentially, or in this case, a list of futures for each of these computations. Okay, so basically, I can then continue computing based on these futures. So I can use client submit. The operation I want to do is a sum, and that should happen on futures. Futures is the list of things that are promises. So it will contain the result of the computation as soon as it is done. Okay. So basically, futures will be gradually filled as tasks in map are finished. And once they're finished, the sum can be computed. So this is quite similar in spirit to what we already saw for concurrent programming in Python itself. Basically, this is building a task graph by hand in a way. More or less clear? And this happens, of course, distributed, so this happens on as many compute nodes as I would like. Of course, this is way too cheap. This will be very slow because a lot of overhead is involved, and this computation is really very, very short. It's just to show you the idea of how that would work. Okay. So basically, I would say Dask is easy to use. It supports out-of-core computation, so you can operate on larger data sets than you normally would be able to or are able to store in memory, and it can do distributed computations. So it has good integration with pandas, with NumPy, and it also is very similar to concurrent futures which you'd have in Python, in the Python standard library. Okay. And it's relatively easy to deploy, especially with Slurm, where you have these heterogeneous jobs, where you can specify the resources required for each individual part of your job. Okay. Performance, if you know what you're doing, can be quite good, but of course that depends on whether you actually know what you're doing or not. And that's a matter of a little bit of experience, and especially keeping in mind what has overhead and what is more or less for free. Let's put it that way. Okay, any questions about Dask? Yeah.
In Slurm file you showed there were specifications of the device cluster.
Yeah.
Does that mean if we submit that job, it also reserves those like additional nodes on the device cluster?
Yeah, so basically everything you specify there will be reserved during your job. So if the first part of the heterogeneous job requires a single core, that will be reserved. If the second part of the heterogeneous job wants two nodes, two complete nodes, those will be available as well. The third part and so on. So everything is available at the moment your job starts and is reserved for you while the job is running. That's the idea. Yeah, exactly. Okay. So if no questions, let me switch windows a little bit. Okay. All right, so we can do parallel programming with Dask, but we have very little control in a sense, since basically this task decomposition is done automatically. And you can't really express anything you want with sufficient, let's say, control in Dask. So if you want to do parallel programming on multiple nodes, then you would need something else. And in scientific computing, that something else is essentially NPI. I'm going to quickly tell you what it is. I'm not going to actually explain this. The reason is historic. So there is a training specifically on parallel programming with NPI, which is scheduled somewhere in April or May. And back in the days, this was a training for Fortran, C, and C++. Now, it has been updated for Python as well. So basically, if you're interested in MPI, then I would say follow that training, even if you are a Python programmer, because it's now for all languages rather than just the classic HPC languages. That training goes into a lot of detail, and you will learn about a lot of things you can do, things you should avoid, and all that kind of thing. So I'm just going to give you a bit of an overview of what you can do with it. I'm not going into the details. You might wonder, okay, why? What's the historic thing here? Well, basically, that's one of the trainings that I give that I did not develop the training material for. So back in 2012, I think, a long time ago, I followed the Train the Trainer program in Stuttgart, which basically means that I'm entitled to give this training and that I'm also allowed to use the training material, which is great, because if you look at that training material, it's a stack of 500 plus slides. Creating 500 plus slides is a huge amount of work. So yeah, at the time I wanted to create training on MPI, And I did have some material. Some of it is in this presentation. But then I followed this train the trainer thing and could use that material, so I just started using that. Okay, but of course at the time that was only for C, C++, Fortran, obviously. But then later on, the person who maintains this material, gives this trainer program, and also gives these trainings elsewhere, added material for Python. So now I also updated my training in the way that I also talk about Python. That's why I'm going to be brief about this part. Okay. So basically, why would you want to do something like that? Well, basically, again, it might be that your data set just doesn't fit in memory. And that in order to process your data set, something like a task graph is not really the optimal thing. Think, for instance, of an application that would predict the weather. Okay, so yeah, if you try to predict the weather for Western Europe or for a larger part of the world, with a decent resolution, you need a lot of data. Okay, that's one thing. The other thing is you also need a lot of processing, because these are partial differential equations which you need to solve, and that is computationally very non-trivial. That's a lot of compute work. So basically, besides the fact that your data set would not fit in the memory of one computer would also not be powerful enough to do all these computations. So you really need to distribute the work. That is one way to do that, is to say, well, okay, I'm going to do domain decomposition. And in this case, that's quite simple. The thing you do is you have your map, you cut it up into regions, and each computer gets to a region. Okay. How large that region is depends on how many computations need to be done, and of course, how much memory is required to represent that region. Okay, so far, nothing too complicated. Now, of course, if each computer would compute the weather only for the region which is assigned to it, which it is doing, then of course you would get a problem, because air flows out of one region into another region. The temperature in one region is going to have an influence on the temperature of another region. That's pretty clear. So basically you see that I can do a step in my computation. I can compute the next time step for my region, but then I need to ask the boundaries from the other region. And I need to pass my boundaries of my region to my neighbors. So you need communication. And of course, a lot of communication is going to be required. This is fine-grained parallelism, because doing a single time step doesn't take that long. Hopefully, because otherwise you're not going to get any meaningful predictions over a long period of time. So basically, each time step is fairly short. So that means that you very often need to exchange information with your neighbors. Okay, so that needs to be done efficiently. And one way to do that efficiently is to use MPI as a communication library and rely on that. And that is the way, the default way of doing distributed parallel computing on HPC systems. There are alternatives, but MPI really dominates. It's also the oldest one around. No, that's not entirely true, but the oldest surviving one around, let's put it that way. Okay, so that's essentially the idea. And now we need efficient, fine-grained and non-trivial potentially communication. So that's something that a thing like Dask is never going to give you. So then you need more work, basically, in order to get that done. So essentially, data needs to be exchanged and state needs to be exchanged. That's the idea. There was in the 90s, there were a number of initiatives a number of frameworks to do that, and yeah, they were varied, and there was a need for standardization. So back in 92 or 95, okay, I have maybe the date on the slide, there was an initiative to define MPI. So MPI is a standard. It's a book, that's it. And there are many implementations of MPI. I already mentioned Intel MPI yesterday, but there are others as well. But all MPI libraries must support that standard, and they do support that standard. So that means that you can switch from one library to the other if that is required for some reason. There's no reason why you couldn't do that. It's API compatible. Okay. So basically, it's you use a library. So you use an API, and traditionally, as I mentioned, MPI is in fact, if you look at the MPI standard, then basically there is a C and a Fortran implementation. There used to be a C++ implementation that has evaporated. C++ people just use C API, so basically that's as such not an issue. Okay, so basically it is a standard, so you can buy the book, literally. I have a physical copy of the MPI 3.1 standard. Currently we are at MPI 4.1, I think, if memory serves. So basically it evolves over time. Features are added, other features are deprecated. It's a living thing. And so basically libraries support it. So typically MPI 3.1 is fully implemented by all libraries. It's not an issue. MPI 4 is mostly implemented by most libraries, but not necessarily everything. So typically standards are backward compatible, something that you could do in MPI 3.1, you can also do in MPI 4. As I said, sometimes things are deprecated, but that takes various generations. It gets deprecated in one generation. In the next, it gets really, really deprecated, and then in the next, it will vanish. So you have always quite transition time in order to switch from a feature to a new feature. It's usually not so much that a feature disappears, it's more that it's replaced by something that is better for whatever definition of better. Okay, so essentially C and Fortran, and many implementations. I already mentioned Intel MPI, which is very good. Also MVPIC 2 is quite good. And OpenMPI is also very good. And actually, there is a typo that should be Open Space MPI, but okay. 60. Right. Okay. What is typically installed? Normally on an HPC system, you will find certainly OpenMPI. That's almost always there. Mostly also Intel MPI, especially nowadays because it's part of one API, which now is much easier to use due to the change in licensing policies. So that's rather interesting. And on some systems, there are special MPI implementations. For instance, if you were to work on Lumi or maybe also some other large-scale systems, so your HPC systems, the very large ones, you may find specialized MPI libraries for that particular hardware. On Lumi, for instance, that is the case, because it uses something rather exotic with respect to interconnect, and they really, really strongly recommend you to use their well, it's not a proprietary library of Lumi, of course, but of the vendor, HPE, basically will counsel you to use their library. Okay, anyway, but again, it doesn't matter. because at the level of the API, they all do the same thing. So your program will work regardless of the MPI library which you link against. Okay, that's great. And there are wrappers, for instance, for Python. And of course, that's what interests us here. Okay, here are some use cases. So in almost all scientific domains you do on the HPC system, you will find applications that rely on MPI in order to do distributed computing. So that's the case for molecular dynamics. That would be the case for all kinds of ab initio computations in quantum chemistry, computational fluid dynamics, astroplasma physics, for instance, also computational biology, some things. So basically, it's pretty pervasive, and it's your go-to for distributed computing. And under the hood, it can also be used by libraries that somehow exploit that. There are a few examples here. So you will remember that I mentioned the BLAS library and LAPAC. So they have their parallel counterparts. BLAS for distributed matrix operations and Scale LAPAC for parallel linear algebra operations. So those under the hood are going to use MPI in order to make that possible. Also, for instance, you might be familiar with the FFTW3 library. Also, that can be used distributively and is using MPI under the hood. Same for HDF5 if you want to do parallel I/O. Again, under the hood, it's going to use MPI. Okay. So you could sort of say that this is the de facto standard in scientific computing when you want to do distributed computing. As I said, it's not entirely true. You have other ways of parallelizing. For instance, in Fortran 2018, it introduced co-arrays. So basically, that would be a way to, an alternative to MPI, but it's restricted to Fortran. There are some PGAS languages which are, or PGAS libraries which are specific. So there are alternatives, but yeah, in practice you don't see them often. Okay, so MPI is something that you want to run on a cluster. So you don't want to run that on a bunch of computers connected with Ethernet because of the fact that I already mentioned your communication is going to be pretty fine-grained. That's what you want. If you want to do that type of communication, that means that you want to do two things. You want to maximize bandwidth. Okay, that's easy. Ethernet can do that, no problem. But you also want to minimize latency. And that's something that Ethernet is not going to do. So for that you need specialized hardware and specialized networking protocols. And basically what you see most on HPC systems is going to be InfiniBand. It has very high bandwidth and pretty low latency. So, for instance, the Barcelona supercomputer is using InfiniBand. Lumi is using HPE specific technology, so that's not InfiniBand, that's different hardware. Okay, so basically, then the next thing is how do you arrange your nodes? And there are several options. If you have lots and lots of money, you can actually do a 3D torus, which is quite nice for many applications, but which is really expensive. We used to have one, but yeah, you can't pay for it in these days. So basically what is mostly used is what's called the FAT3, basically because that's something you can at least afford in a normal data center. So also, for instance, the Barcelona is organized in FAT3. So it's not as if it's not okay. You can do better, but FAT3 is perfectly fine. But the bottom line is that it is really, really, really expensive, such a network. And if you look at procurements, for instance, here at KU Leuven, if a cluster is acquired, then typically between 16 and 18% of the budget goes to this hardware. So it's a huge chunk of cost of an HPC system. So yeah, that is unfortunate, but yeah, that's what it is. And you need it for that these computations that need fine-grained communication, that need very intensive communication in terms of time. Okay. So basically, that's the key here. Processes need to interact often. If they don't need to interact often, you don't care that much about InfiniBand or about latency. But if they interact really often, then you start thinking about this carefully. Okay, so what's the programming model? So essentially, it is shared nothing. So basically, your application consists of multiple processes. Those processes don't share any data. So if they want to exchange data, or if they want to exchange state, they do that by exchanging messages. So a process can send a message to another process. That's the way that works. So basically, each process has its own data. Okay. So here's an example of a Python MPI script. So basically, I import MPI from MPI for Py. And everything you do works via a communicator. So a communicator you can view as kind of a communication device, network thing. Compare it to a phone network or compare it to a mail service. Depending on how you're using it, it seems like the one or the other. And then basically, based on that communicator, I can get a few things. I can get the rank and I can get the size. So the size is going to be the number of processes that I'm running. So that is the number of things that happen in parallel, if you want. And the rank is going to be a number between 0 and the size minus 1. So that's an identifier of a process. So each process has its own unique rank. And that's just an integer, a number between 0 and the number of processes I'm running with. So basically, then this is printed. And how do you run that? Well, very easy, MPI run. You specify the number of processes you want, in this case 4, and you execute your script. Okay. And then, depending on how you do this, you can run processes on the same node or on different nodes. So this is for distributed computing. I can use any number of nodes I like. Okay, so this was really, really simple. What you get is something like this. And then, of course, the order here is going to be random because all these things happen independently. So depending on which process just accidentally executes the print first, is going to be the first line to output, etc. etc. Okay, that was easy. So basically, as I said, you always use a communicator in order to send and receive messages. And by default, there is one, which is ComWorld, and that basically contains all the processes which you are running. So this one is always there. MPI ComWorld is always there. You can get the number of processes, you can get a rank, etc. As I already explained. And so basically, this rank can be used in a number of ways. On the one hand, it can be used in communication to address something, a message, to another process. That's one usage for this rank. Another usage for this rank is, of course, task differentiation. So, for instance, I could use that rank in order to compute the boundaries of a part of an array I'm supposed to operate on. So I could use the rank in order, in my weather application, to figure out which region I'm actually computing for, and hence which geographical data I should load, which weather observations I should load in order to initialize that computation. So that's another usage of the rank to differentiate between processes. Here is an sorry. Here's an example of that, in the sense that if rank is 0, I'm printing the total number of processes. All the other processes will not do that. Only the one with rank 0. So this is what you get. Everyone is going to print hello from, and process 0 is going to print the number of processes. So that would be an example of that. Okay, so this we know. Yeah, so basically, you, as a process, you ask for your rank, you ask for your size, for the size. That's a local variable. So that's sort of private information if you want. Remember, shared nothing, so. But you know that you're the only one with that rank. Okay. So now, in order to communicate, as we said, we need to use the communicator. And there are several ways of communicating. You can communicate peer-to-peer. Basically, that means process 5 sends a message to process 8. Okay, that would be peer-to-peer. You can also communicate collectively. So, for instance, you have a value. Each process has a value. And a process wants the sum of all those values. So reduction over all processes. So that would be collective communication. Everyone does a call to a function, and that sum will be computed. Information is needed from everyone in the communicator. They all have to collaborate in order to get that done. So that's collective communication. And then there's also one-sided communication. So basically, I can say, well, okay, give me the value of this particular location in memory of process 5, and I'm not process 5. So this does allow for a sort of shared memory communication if you want. You could view it that way. It's not quite the same, but you could view it a little bit like that. And basically, that is another option which you have in MPI. And in fact, you can do shared memory programming in MPI as well. It's not so popular. Usually, if you want to combine shared memory programming and MPI, you do the shared memory programming in OpenMP and then the distributed programming in MPI, but you can do the whole lot in MPI. But it's not so popular. It's a bit more difficult, essentially, than using OpenMP. That's why it's not so common. Okay, so communication can be blocking and non-blocking. Remember, with multiprocessing, we had blocking calls and async calls. Similar here. So we also have two modes of communication. So here's an example of peer-to-peer. So essentially, I've got a process in the role of sender, and I have a process in the role of receiver. So the sender is going to send something, the receiver is going to receive something. And the send buffer, the classical name for it, is essentially just an integer in this case. So basically, the nice thing about MPI for Pi is that you can send almost any Python object as a message. That's something that's possible, but much harder in other programming languages. But in Python, it's pretty trivial. The limitation is that that object which you want to send must be pickle. You must be able to pickle it. If you can pickle it, you can send it. That's the idea. So pickle is a Python-specific way of serializing objects. You can't serialize arbitrary objects. They have to have certain properties and certainly not do certain things, but you can pickle quite a lot. So that is quite convenient. Okay. In Python, if you do peer-to-peer communication, if you do a send, you have to do a receive. So, well, the process that receives must do the receive. So it is kind of a handshake thing, if you want. I send you something, you have to receive it. Both parties are involved. Okay, let's not go into the details. Because peer-to-peer communication is not what you typically do. It is not so very efficient. It's much more efficient to do collective communication. And collective communication, as I said, involves a group of processes who all do the same thing. So basically, there are a couple of things you can do. For instance, if a process has a value and all the other processes also need that value, it can be broadcasted. That's one operation. Another operation is I have a number of values, but they are different for each process. So I scatter them to the other processes. So that's a scatter operation. A gather operation is just the opposite. Every process has a value I want. All those values are distinct. I want them all. Then I do a gather. And when I say I mean me and all the other processes do the same operation. That's always the case with collective operations. And then you have convenient things like a reduction. So you could see that as I first gather data and then I reduce it to, for instance, a sum or a product or something like that. So there is a single function call for that, and that is a reduce. And then you have things like all to all, which basically means I need to send a distinct value to all other processes, and I need to receive a distinct value from all other processes. So that would be an all to all. That's a very unpleasant operation. It doesn't scale, so you're going to be very unhappy if you have to have that in your code. But anyway. So collective operations are typically also synchronizing because they make sure that everyone is sort of on the same page. Okay. Let's not go here. Again, there is a separate training about this with nicer slides. Okay. So this is about the reduce. So reductions you can do some product, what else? Minimum, maximum, all that kind of thing. So basically, there are quite a number of operations for reducibility. Okay, all to all, blah, blah. So just to, as an example, this is again computing pi. So I don't quite remember how I am. So basically I compute pi differently here. I'm not throwing darts anymore. I'm going to do a quadrature. So basically an integral, which is also going to give me pi. So basically the process 0 typically plays a special role. It's usually dividing the work and so on, doing data aggregation, but that's arbitrary, but convention. So basically, process 0 is going to, for each process, determine the integration boundaries. And it's going to, then each process is going to do its part of the computation. And then the results will be gathered by process 0, which is going to the output. So that's basically the idea. Of course, this is artificial because just based on the rank, each process could compute its own domain. But yeah, this is just for demonstration purposes because I wanted a scatter in this example. So this is what it would look like. So let's perhaps go over it at a high level. So first we have some initialization, and that's done by all processes. So each process is doing all of this at the same time. So basically, they're all initializing all these variables. And then you have something that happens only for a special process, the one which is the root. And the root in this case would be process 0. Would be process 0. So process 0 is going to compute something that the other processes are not computing. Okay. Then, when it has done that, and all the processes are get here as well, then there is a broadcast. So it's going to send information to all the other processes, which process 0 actually has, and the others don't have that. Okay. So it's going to send n. Okay. It's also going to send verbose, so it's going to do two broadcasts. And then it's going to do a scatter. So basically, well, two scatters. It's going to send the lower and upper index to each process. All right. Then everyone is computing the its own sum, and then in again the root, the reduction is happening. So basically, all the partial sums are summed together and are available in the root process, which outputs it. So that's basically the idea of this application. It's a very silly example, and of course, just to show a few of these operations. Okay. So basically, in Python, as I said, the nice thing is you can send anything that's pickable. Of course, that generates overhead. So do you want to do that? Depends. Not really sure. Then, there we have our buffer protocol again. Any Python object that implements the buffer protocol can be sent as well, easily. So that's great because that means NumPy arrays again. Okay. The API is a bit more involved, but okay. So this would be communication send receive. Let's not go there. Basically, that would be with a NumPy array as a buffer. Okay. Let's not go into details and reduce. So there are a couple of limitations, but I think by now they have all more or less vanished, of things that don't exist in MPI for Pi, but that do exist in the standard. I think almost everything now actually is now complete. Okay, let's not go here. We're going to talk about this in this presentation. Too much details. So one of the things you can do is overlap communication and computation. So basically, it's a little bit like using futures. Essentially, you can send data and meanwhile do computations. You need to take some care. It's not obvious also that it works, but often that can give you better performance. So that's why you actually have non-blocking communication and so on. Let's not go there. Okay. So MPI for Pi is really a very good library. And I also cited it as an example of a library that uses Cython to generate wrappers. And you understand why that is useful here, because basically you will have many function calls. So if each function call starts to generate overhead, that is going to be a pain at the end of your computation, because all that overhead is going to add up. So that's why for MPI for Pi, developers chose, well, okay, let's really do the best we can. Okay, it's going to be a lot of work, but it will pay off, because this is a very important library, it's a fundamental library in HPC. So they really went all the way and did the wrapping very, very, very carefully. Again, lots of work. Do you need to go there? Probably not for most things, but if performance matters, then Cython is indeed the way to go. Okay. So the way you use MPI for Pi is a little bit different from what you do in C and Fortran. It resembles much more the interface which used to exist for C++. So the MPI for Pi API has taken quite a bit of inspiration from the no longer existing C++ API, which is really a lot nicer than what you have to use in C or in Fortran. But anyway, the documentation is not great, to be honest, but well, I think it has meanwhile improved a bit, but when last time I checked, it was still underwhelmed with MPI's for Pi's documentation. But yeah, who likes writing documentation? So yeah, I can sympathize. Okay. Any questions about this? Probably a lot, but again, if you're interested, just attend the parallel programming with MPI training. That is much more extensive, and you learn all the nitty-gritty details, much more than you ever want to know about MPI. Okay. There are yet alternatives. So again, we want to process data. Again, our data is too large. We can do that with Dask. We can also do that with Spark. So Spark is an Apache thing, and so free and open software, etc., etc. Apache has these huge projects, which some of you've heard about, and basically Spark is one of them. And Spark comes in a number of implementations. Let's put it that way. So there are wrappers around Spark in several programming languages. So what is the issue? The issue is big data. Big data used to be a buzzword. It's gone now as a buzzword, but yeah, the big data is still there. The point was that many things which were called big data weren't big data, but okay. So in big data, you can have a number of orthogonal properties that make something potentially big. So the one which is obvious, of course, is for you. How large is your data set? Clearly, if it's a large data set, then it's a big data problem. Yeah, fairly straightforward. But there are other dimensions as well. So you also have velocity. In other words, how fast does my data come in? And of course, in scientific programming, there are use cases for that, but not that many. But for instance, one of the areas where that would matter is data processing from experiments. How fast does your data come in? Depending on what you're doing, that might be really, really fast and really, really large volumes. For instance, if you have a detector at CERN, yeah, you get really lots of data really, really fast. So that is something that also in scientific computing happens. Not that often, but it does happen. And then another V, notice all these things start with V, that is not a coincidence. The third V is variety. So basically, your data may be scattered around many data sources. So rather than having a single large data source, you might have many places where your data comes from, or many formats your data rolls in. Sensor data, for instance, would be one of those examples. If you have a sensor network, then you have quite a bit of variety. And of course, you can combine all these. These are orthogonal, so basically you are somewhere in a two-dimensional space. So you might have high velocity and a lot of variety, or a lot of high velocity and a big volume, or all three. I mean, yeah. So solutions were required, and one solution is indeed Spark. So this remark, usually not that big, but that's basically because at the time, since it was a buzzword, everyone came to us and said, yeah, I have a big data problem. Okay, how large is your data? Yeah, it's a gigabyte. Okay, that's not large. I mean, in HPC terms, that's just a small problem. So yeah, stop bothering us, just do something and come on. So basically, this is something that at that time you saw quite a lot, that many people thought they had big data, but yeah, I mean, yeah, no, really, no, it's small data set, sorry. But yeah, okay, whatever. Anyway, what you want to do, again, is analyzing data in a distributed fashion. So basically, your data is, again, too large to be stored, so you need to partition it somehow and also partition the computations. We could do that with Dask, and Dask is a very nice system. We can also do something similar with PySpark. Okay. The data can also be stored distributed, so that's a bit different from Dask. You can do that, but okay. So Apache thing which you certainly have heard of, well, okay, which by now you might not have heard of anymore, because again, that's a while ago, was Hadoop, and Hadoop, of course, is still in production. That's not the point. But basically, the problem with that was that the computational model was pretty primitive. So what you could do essentially was a map reduce, and then some things on top of that, but not that much. So the computational model was really, really limited. And of course, for certain operations, it's good enough. So if you remember my Dask example where we did the group by followed by me, that's something that you can happily do in Hadoop. It's a simple operation. It's just mapping and reducing, easy. So that would fit well. But other operations, nah, not that much. So basically, it has a whole ecosystem around it, its own file system, HDFS. It has schedulers, different schedulers. It has resource managers. It has several distributed databases. It even has a machine learning library built on top of it, and so on. So it's an ecosystem which is really quite extensive. But deploying it on a cluster is a bit of a nightmare, since this distributed file system, this HDFS thing, needs daemons on storage nodes. Okay, your computation also needs daemons for the worker nodes, and then you have a lot of, well, at least one or two management nodes. So basically, there is a lot of stuff going on, which is really, really non-trivial to set up and to run on an HPC cluster. Indeed, heterogeneous jobs on Slurm would help, but still, it's quite a lot of complexity, because you have to bring up your Hadoop cluster inside of an HPC cluster. So if you want to do this on HPC, you're not going to be so very happy. It can be done, it has been done, but it's rather unpleasant, and of course it's pretty error prone. So yeah, that's a bit of a problem. Okay, So performance-wise, you've got communication via the file system. So when a certain task is done, results get written to HDFS. Okay, that's file system operation. That's something you don't want to happen too much on HPC systems. So your performance is not going to be great. So yeah, you can store it in a database, great, but then you also have to have that running. So okay, things get complicated. And then one of the drawbacks of Hadoop is also that the scheduler which they included is smart, but not so very smart. So basically, you have a lot of data movement between storage nodes and worker nodes, or between different worker nodes, because the data is suddenly required for computation elsewhere, so it just moved from one node to the other. And okay, if you have a clever scheduler, which takes that into account, then you can kind of mitigate that. But the Hadoop scheduler doesn't really do that. So efficiency-wise, this is not really your friend. And then, of course, the computational model is the same as that for Dask, so it's a DAG. And that may potentially be a limitation. Since you don't have iterations, unbounded iterations, you don't have a while loop in a DAG. So yeah, that is also potentially a limitation which you might not be able to overcome. So that's why after a while people realized, okay, Hadoop is nice, but we need something different. And that something different was Spark and another Apache project, which is quite successful. So it tries to, as much as possible, in memory processing. So that's good because we like that. That's great. Not too many files, no file I/O operations. That's good. Sounds good. Now, if that's not possible, then there is efficient spillover to disk. So basically, once the working memory is full, it's going to store part of the data, reread part of the data, and so on. So that out-of-code thing is supported by Spark. And it's smart in the sense that it tries to minimize this. So the computational model is essentially do what you want. Okay, with restrictions. If you want performance, you don't do what you want. Then you have to sit down and think a little bit what makes sense. But in theory, you could do anything you want. So you're not limited to computations that can be translated into directed acyclic graphs. You can have cycles if you want to. Okay, so the basic building block of the whole thing are RDDs. So basically, resilient distributed data sets. Okay, you can sort of think of that as a data frame with two extra things, the R and the D. So basically, distributed is quite clear. That's similar to a Dask data frame. Your entire data frame can be split over multiple nodes. That's the distributed thing. Yeah, okay, that's nice, but not exciting. The R is kind of interesting, resilient. So basically, if you have a shard of your data frame, so a chunk of your data frame, there is not a single copy, there are multiple copies. Okay, that is for resilience. So essentially to make your computation robust in the sense that if a node goes down, of course, it takes with it all the chunks of your data frames which are partially stored there, but there will be a copy of those on other nodes. So that makes it more resilient, which is nice, but it has another side effect. And that side effect is also that, of course, since that data is already present on more than one node, it also saves a bit on data juggling. Because if a shard is somewhere in two places, I can choose to do a computation on that in one place or in the other. So that gives the scheduler a bit more leverage, a bit more the way for creativity and for optimization. So that's actually rather nice. How can you program Spark? So Spark itself is a Java thing. So obviously you can program Spark in Java. Java and scientific programming are not necessarily the best friends. There was a time when that was an option, but nowadays, except in bioinformatics, I don't think that Java is still used. What you can also use is Scala. Scala is essentially a functional language based on top of Java. I've never looked at it. Yeah, it's not something that is used in HPC, so I'm not paying attention. But you can use Spark also from Python and from R. So the features which are implemented and also the maturity basically go up here. So Java is, let's say, the gold standard. It has the most recent features. It's the most tested, the most robust. Scala is a little bit behind. Python is again more behind, and R is also lagging. So basically, that's a little bit how that works in practice. So of course, what we're interested in is the Python layer, Python implementation. So this is the infrastructure. So this is similar to the diagram I showed you when we talked about Dask. So we've got a lot of workers, and those are essentially processes that run on multiple compute nodes. Okay, then you also have a driver, and actually the driver is going to communicate with all these nodes. So there is no scheduler in between. So this is a bit different. The driver essentially is client plus scheduler in Dask terms. Okay, and then of course, since these are workers on compute nodes, they can of course use a distributed file, a shared file system, and the driver of course can also access that file system. So basically, that is your computing model here. Okay, so then the question is, how do we work with it? Well, basically, you will recognize quite a lot of concepts that also occur in Pandas and hence in Dask, but there are some significant differences. Okay, so to create an RDD, you use a context, which you need first to create, and then you can call, for instance, a function such as text file, others for other data types, and so on. So basically, similar to the read CSV, the read Excel, etc., which you find in Java. Okay, you can also create an RDD from list-like objects. So in this case, to drive the point home, I'm just using a NumPy array as the source of my RDD. Of course, doing this implies that my entire data actually fits in memory. Clearly, because this NumPy array is going to be generated. So if I make that, let's say, 10 billion elements, I'm going to run into trouble. Then this is not the way to generate that data frame. That's pretty clear. Okay, and it can also be read from sequence files, so basically binary files such as Parquet and so on and so on. Okay, so you can look at values. So for instance, you can get the first value, or you can get 5 values, or you can get a sample, in this case with or without replacement, of the size of 50. So basically this is just looking at your data, looking at what's in that data frame. Okay, and this is an action. You can also get all the values as a list. Then you do collect, But of course, you should realize that if this is a huge RDD, suddenly instantiating that as a list might mean that it doesn't fit in memory. So a collect only makes sense when you know that the amount of data which you're collecting is not too large. Otherwise, of course, this is not going to work, that's clear. And basically, that's again an action. Okay, yeah, the remark I already made. So, of course, you can also get other meta information, like how many elements are there, in fact, in your RDB. So you can do a count. And you can save values to a file, for instance, as a text file or as a sequence file, and so on. And that, again, would all be actions. Okay, so making RDDs, saving RDDs, looking at RDDs, all pretty simple, all pretty uninteresting. This is a bit boring. So what can we actually do? So one of the things we like to do, and that's something that we could do in many frameworks, is simply mapping a function to each element in an RDD. And in this case, it's quite simple. I can pass in a lambda function, and that will essentially map all the data to its square. And this can happen distributively, which is kind of nice. And notice this is a transformation. So a transformation is something that changes your RDD. An action doesn't change it. And that distinction is pretty important. That's why for anything I put here on the slides, I'm indicating whether it's an action or whether it's a transformation. Okay, you can also filter elements, again, based on a lambda. In this case, that lambda should return true or false, depending on which criterion you want to implement and on the element in the RDD it's applied to. So, of course, this is again a transformation, since this creates a new RDD does something to an RDD. You can also do reductions. So basically, you have a reduction, a sum reduction here. So you get elements A and B, and of course, one is the accumulated value, the other is the new value, and the sum is computed. You can directly compute the sum or product or minimum or maximum. All of these are supplied, those are implemented as separate functions, of course, but you can program your own reduction if you want. And these are actions. So again, that's not going to modify your RDD. That's just going to use the values. Okay. So basically, all these operations are local. So computing the maximum is in fact a local operation. What do I mean? Well, if I have a chunk of an RDD, I can compute the maximum value for that chunk. And then the only thing which needs to be done is to find the maximum of all the maximum values, so of all the chunks. So it's not entirely local, but the heavy lifting is local. Because, okay, how many chunks will there be for your RDD? 100. So that means that I globally have to take the maximum of 100 values. Yeah, that's easy. While each chunk in itself could contain 1 billion values. Yeah, that takes a while, but that happens locally for each chunk separately. So that's why this is pretty cheap. Almost no communication is required between workers for these type of operations. And that, of course, makes it cheap. The fewer communications required, the better my performance, because I will have less overhead. That's pretty clear. So all these local operations are quite cheap. And the same applies, by the way, for the map, because I can do that locally. I can modify my data frame chunk in place. No requirement of on communication. So all of this is cheap, and that's important to realize. Why? Because at some point you need to order your operations, and then of course what you want is a flow where you start out with very large data, which you try to process as much as possible in place, then reduce that to a data set which is smaller, for instance by a group by the aggregation or something like that, so that you get a smaller data set. Then you try to do the operations which require a lot of communication. So if you think in those terms, you can optimize your data flow in such a way that you minimize communication. So that's not done for you automatically. That is something that you need to keep in mind when you're developing Spark workflow. Okay. Everything is lazy. So basically, an action, of course, yeah, that's not lazy. You get the result. But if you do a transformation, that's not done immediately. That's only done when it's required. And that again gives some leeway for optimization, because at the end of the day, if the driver analyzes, well, when the driver analyzes your workflow, then basically it can notice, okay, there is a quite expensive operation here, but in fact, I don't need to do it. For instance, suppose I have a huge data set, the one which we had in the CSV files. Okay, I do the group by, I do the mean. And then I do a filter where I only ask for month number 1. Yeah, then I might want to reorder things and first select everything from month number 1, skip the group by, and compute mean. Potentially much cheaper, depending on, now in this case, computing a mean is fairly cheap, but make that a very heavy operation, then reshuffling that actually makes a lot of sense. And that is something that the driver is actually going to do for you. It can only do that when these operations are implemented lazily, and that is indeed the case. So that's why that helps. You can also do set operations, which, if you're in data science, can be quite useful. So, for instance, a union and a dissection, or a distinct. So basically, distinct means gives me the unique values. Okay. These, of course, are transformations. Notice that there is no set difference. The problem with set difference is that it's very expensive. That is a very non-local operation. Every worker needs to know everything that all other workers know. So you see, you can only do that when you really have a lot of communication going on, and that's something that you really, really want to avoid. So that's why there is no set difference. A very useful operation is a Cartesian product. So you've got two RDDs, in this case V1 and V2, symbolically, of course. Then the Cartesian product is going to be the tuples of V1 and V2. So basically, you get for every value of your first RDD, you get a tuple with every other value. Well, you get a tuple per value for the other RDD. So the size of this Cartesian product is, of course, going to be the product of the size of the two RDDs you start from. But this is a very useful operation. Of course, again, a transformation, so again, lazy if possible. Okay, so thinking in terms of key value pairs is pretty crucial in Spark. So that's something that you conceptually need to get your head around in order to do certain computations. Okay. So it can be convenient, but often it's just downright necessary. So you can, for instance, use that to label data for aggregation. So for instance, I've got a data, an RDD here, it's just numbers. And then I compute the signs. So basically, that's just a map operation, and either it's positive or negative, depending on the sign of that particular number. Okay, nothing special happens. These are cheap operations. Okay, but then I can do a reduce by key. So basically, I'm going to have a reduction, a sum reduction. Okay. And then where are my signs? So this is weird. Okay, then I'm collecting, but okay. Wait, there's something not right here because I'm not using signs. So that is a bit weird. Here is a missing argument, which is probably signs, which I need. So this code is not correct. This can't be correct. Something is missing. I don't remember offhand what this should be. I'll look in source code later. But basically what you would get as a result is essentially the sum for all the positive numbers and the sum for all the negative numbers. And that is based on the key. So basically that is based on the wait. No, it's fine. Okay, sorry, I didn't read it properly. Because you have to look carefully at what the lambda function does. The lambda function in the map operation. So it's going to take the original elements in data, but it's going to return a tuple, a two-tuple. The first element of that two-tuple is either pos or neg, but the second is x. So I now have a data frame that doesn't as such contain the signs by itself. So the name of the variable is questionable. But the important thing is that it also contains the value. So it contains a label and a value. And then based on that label, with the reduce by key, the first element of that tuple is the key. So I will get two sums, one per label, because in this case I have two labels, one per key. So basically I will get one for pos, I will get one for neg. Sorry, I should have read this properly before saying that it was wrong. It's actually correct. And then at the end of the day, we do a collect and we get our results. And this will be a very small RDD with just two elements. Both of them are tuples. One of them will have as a key pos, the other will have as a key neg, and each will have the value, which is the sum of the positive elements and the negative elements respectively. So you have quite a number of key value-based operations. So you can group by key, okay? You can reduce by key. So I could have done, I did a reduce by key. You can do an aggregate by key, a sort by key, a count by key, etc., etc. So basically you see, just due to the number of these functions, that this is really a key thing. Sorry, this is very feeble pun. In reasoning about how to program Spark. So basically, you very often have to translate your problem into something that can be expressed as key value. That's the crucial approach to doing something useful with Spark. At some point, I sat down by way of exercise and figured out how to do a matrix multiplication in Spark. That's a good exercise. You need to think in terms of key and values, and basically you get it done if you understand how to do the things with keys. Okay, so of course, all these operations are by nature non-local. because you have these keys. So here a lot of inter-node communication, inter-worker communication is required. So if you do this on large data sets, you're going to be unhappy. So that's what I mean by ordering your, or creatively, efficiently creating your workflow. These type of operations should go near the end of your computation as much as possible. Because then typically you have smaller data sets because you've already done reductions, and then it's easy to do them because then computations are much less. Okay, so you have also join operations based again on key value pairs. So I've got two data sets, data 1 and data 2. So essentially we are assuming that they share keys, but that they have distinct values. So you can do a number of things. You can do a join, and then basically what you get is a new data frame where for each key there is a tuple of the values of these two data frames. This will only return the keys which are present in both data frames. So you will lose data with this operation, which may be your intent or not. You can also do an outer join, a right join and a left join. So basically inspiration or a full outer join. Basically the terminology comes from SQL, where you have the same thing done with tables. So essentially a left join means that all the keys in the left, so basically in data 1, will be present. But of course that means that there will be no values in the second element of the data tuple for those keys which are missing in data 2. Right join does the same thing, but swaps the roles of data 1 and data 2. And full outer join will contain all the keys in both RDVs and null values for everything that's missing. Okay, so this is exactly the same as you would have in SQL. This is exactly the same as you have with the merge in Pandas. It's the same thing. Okay, so again, that's a transformation. So again, it's lazy. Okay, you can also have broadcast variables. So basically that's a little bit like a shared variable, but be careful, that's read-only. And that's just cached on worker nodes. So basically that can be parameter settings for algorithms, that can be input data for certain parameter sweep scenarios, these kind of things. But notice it's read-only. So you create them easily, you've got your parameter, and then you broadcast that using the Spark context. Spark context knows about all the workers, so it's going to do that for you. After that, you're not supposed to change a global params. Okay, so basically, if you want to use global params, you just use value. So this resembles the value object which you had in shared memory with multiprocessing. Only there you had the ability to log them and hence to modify them. Here, no, you can't modify. They're read-only. Okay, then there are also accumulators. So those are update-only variables. So for instance, a counter. So those can, of course, be modified, but that is done in an atomic way. So the update is atomic because there is a layer around it which ensures that. So basically, you can use that for cumulative sums. So for instance, here I create an accumulator initialized to 0, and then I can update the value simply like this. So this seems to be a non-atomic operation, but if you would look under the hood, then in fact this is atomic, since plus equals maps to a certain number function And hence, in that, I can actually ensure that this is locked, gets updated, and is unlocked automatically. So you can do that in Python. Multiprocessing decided not to do that, but they decided to do that in PySpark. Okay, and then the final result you get with accurate value. Don't use closures for this. For those of you who know what Python closures are, you might think, well, okay, I'm going to use a closure. Don't do that. It's not going to work because of pickling and so on. So that is not going to fly. It can't fly. Okay. So the computational model is pretty rich. You can do quite a lot, but you have to translate often from your original approach, from your original algorithm you have in mind, to this key value type of thinking. Okay. I would say it's fairly easy to use. It's reasonably easy to set it up on a cluster because, again, it's a bit like Dask. You don't need that much infrastructure. You just need to run your workers, you need to run your driver, and essentially you are done. So basically, that is reasonably easy. You have to use it judiciously. So if you are naive, you're not going to get any performance. That's quite clear. You have to really understand what you're doing, really understand how the order in which you do things influences the computation time. And the crux is minimizing communication. That's what you have to be very careful about. So anything that is a transformation, anything that is non-local, especially non-local transformations, are potentially bottlenecks. So they should, as much as possible, go to the end of your computation. But still, there is quite a bit of overhead. Okay. So basically, one of the things that I said is, okay, you have these RDDs, and the R4 resilient means that there are multiple copies of chunks of data floating around on your compute nodes. So that's great, but as your data size, your final RDDs are going to be computed, then of course you may end up with very small chunks in many places. And that's not what you want. You would prefer to get somewhat bigger chunks in fewer places. Or you would like to optimize your placement of your chunks, and that is a shuffle operation. So basically, as I said, non-local data, for instance by key, can be a problem. So basically, a shuffle is transferring data between workers, and that's pretty expensive, as I already said, so order of and so on. So basically, RDDs can be repartitioned. So as I already said, suppose that I've been reducing my data sets, now I have many partitions, but they're small, so I would like to regroup them. That of course is quite a lot of communication, but it might be worth it. If I keep on processing, it might be worth to do that. So that's exactly what this repartitioning is doing. And that's essentially also this coalescing. So basically, it's expensive, but it may pay off in the end. You also have caching. So basically, partitions may be dropped from memory to disk to free up memory. So that is something that you can do. But they can also, if they can be recomputed, they can also be completely deleted, and then, if necessary, recomputed later. So that's something that can happen under the hood, basically to conserve memory and so on. So essentially, you can steer that a little bit by saying that this should be cached. So this RDD, you're indicating this will be reused later. So you're telling Spark, if you can cache that, it's a good idea to do that, because 50 lines down the road, I'm going to use this thing again. If then you have dropped it from the cache and you need to recompute it again, it's going to be expensive. And there are several strategies for that. So you can do memory only. So you keep as much as possible in memory. It can be memory and disk. So that means overflow to disk if necessary. So your result is still there, but retrieving it is slow, but at least you don't need to recompute. And other things is memory serialized, so you get better memory efficiency, CPU intensive read. So basically, this is a bit similar to the arrow format, if you want. And then memory only 2 means it's in memory, but on 2 workers and so on. So basically, you have quite a lot of leeway there of how to do this. So of course, there are much more details about Spark. So this is just to give you a bit of a flavor of how that works. What can be useful, for instance, is SQL context, and essentially that allows you to create easily data frames a la pandas from these sources such as JSON files, also directly from databases, or for instance Parquet files and so on. There is also a machine learning library, MLlib, so that has quite a number of machine learning algorithms implemented. Don't look for deep neural networks, that kind of thing. That won't be there. This is more for the classic machine learning algorithms. So all kinds of statistics, hypothesis testing, and so on. Linear models, naive Bayes, decision trees, forests, and so on. The decomposition methods, so basically dimensionality reduction, pattern mining, that kind of thing. But yeah, don't expect deep neural networks there. And then what's also quite interesting is it has also an extension for processing graph formatted data. And that's quite interesting because that's also something that is typically non-trivial. So PySpark definitely has quite a lot of potential. Of course, mostly in data science. This is not for each and every domain, but in data science, it's quite interesting. Okay. I added something about I/O. Okay. So let's just call this a reminder, because actually in the training on workflows on HPC and best practices in data science on HPC and so on, I talk in a lot of details about that. So basically, this is mostly a reminder. I/O is pretty expensive. Reading many small files on an HPC system is going to get you hated, because you are going to slow down the file system, which is a shared file system, and performance of the whole system is going to drop. So that's something that you need to be aware of, and that you should try not to do. So basically, try to group small files into large files, so that you can just read a single file rather than a million small ones. That's quite important. Also, your file format matters. If you have a data set in CSV format and you read that many times, please convert it to Parquet or to Arrow. That is going to be much faster, and it will reduce your compute time because you're not waiting for I/O, and it will also reduce the load on the file system, since Parquet is compressed internally. So basically, keep that in mind, that small files, many small files are not really a good match with HPC file systems. Also, I/O operations in general, don't do many small reads or many small writes. Try to group them into larger read and writes. Okay. So basically, this is an example with NumPy.io. Let's not go there. But as you can see, if you do a binary read versus the same data in textual format, you gain a factor of 35. So we are not talking peanuts, we are talking lots of time here. This doesn't really matter when you read that file once, but if you read it many times, then it really adds up. Okay, yeah, distributed I/O, let's not go there. And let's not talk about HDF5 here, because we already did that in Scientific Python. And which one is this? Is this H5Py or is this? I have to check that. Okay, let me skip all this. So if you're interested in parallel I/O with HDF5, here's an example here. So, okay, we're at the end of the training. So if there are any questions, please ask. Otherwise, we conclude. At the moment, there are no questions online. Are there any in the room? No. Okay. Are there any online? Apparently not. Okay. So in that case, I hope it was somewhat useful. Hope to see you in some other training, perhaps tomorrow when we talk about GPUs with Python. And yeah, have a pleasant rest of the day. The session has been recorded, as I mentioned yesterday. So the recording will be available by this evening or tomorrow. So if you like access to it, just drop me an email and I'll send you the links as soon as the videos are processed in Zoom.
The presentations you have here, they're up to date on the GitHub?
Yeah, so basically for the presentation and also the source code, everything is on GitHub. Yeah, no problem. And as I mentioned, there is much more in the source code than I have time for in the presentation, so there are quite a number of more detailed things which are there and not elsewhere. All right.